Spooky communication across light years, the Bell test experiments. You might be lying in bed right now, thinking the world around you is quiet and still. But somewhere, perhaps in a lab in Europe or a satellite in space, particles are whispering to each other, not through wires, not through signals, but through something stranger, invisible, instantaneous. That's what the Bell test experiments tried to measure. And what they found changed how we see reality itself. It started with a question: can particles really know what their twin is doing, even if they're separated by entire galaxies? Einstein said no. He called it spooky action at a distance. He believed the universe couldn't be that weird. There had to be some hidden rule, something underneath it all, like a backstage pass that explained the trick. But John Bell didn't agree. He wanted to test it. And so, in 1964, he wrote down a mathematical formula, a kind of trap for quantum mechanics. If the universe played fair like Einstein believed, then any particles would follow certain limits. Those limits became known as Bell's inequality. Decades later, scientists put that idea to the test. They took a special type of particle, like photons or electrons, and created pairs that were entangled. One went one direction, the other went the opposite. Then, in distant locations, researchers measured something called spin or polarization, basically a quantum coin flip, heads or tails, left or right. If Einstein was right, each particle already knew how it would land, like a pair of gloves. If you find the left one, the other must be the right. Simple, local, classical. But the results said otherwise. The measurements didn't match up with any glove-like explanation. Instead, the outcomes were linked in ways that violated Bell's inequality. The particles weren't just pre-programmed. They were reacting in real time, even when separated by vast distances. It was as if the particles were connected by an invisible thread, communicating faster than the speed of light. And yet, there was no actual signal. No message, no force we could detect, just a perfect correlation that defied logic. People argued. Maybe there was some loophole. Maybe the detectors were biased, or maybe the particles were being watched in ways we didn't understand. So the tests got tighter. They closed the detection loophole by making sure they captured enough of the particles to be statistically solid. They closed the communication loophole by placing the measurement devices far enough apart that light couldn't travel between them in time. They even randomized the settings of the measuring devices at the last possible second, so nothing could cheat. And still, the entanglement held strong. The experiments confirmed that quantum entanglement isn't just a theoretical idea. It's real. It happens. The universe doesn't behave like a machine. It's more like a mystery that doesn't like being solved. There's no faster-than-light communication. You can't use it to send messages, but the connection is there, waiting, a non-local thread that links particles in a way we still don't fully understand. What does it mean? That's where things get strange. Some say it proves the universe is fundamentally non-local, that space itself isn't as important as we think. Others believe it hints at a deeper layer of reality, a hidden level beneath the quantum foam. And some just lie back staring at the dark ceiling and think, what if everything is entangled? What if we're all connected in ways we can't see? What if right now, somewhere, somehow, another version of you feels this too? Don't answer. Just drift. The night is long and we're only just beginning. Quantum teleportation. So here's where things start sounding like science fiction. But it's not. Quantum teleportation is real. Not like beam me up, Scotty teleportation, but the kind where information gets transmitted without anything physically traveling in between. It works like this. Take two particles, A and B. Entangle them. Then take a third particle, C. This is the one with the unknown quantum state we want to teleport. C interacts with A in a specific way, through what's called a Bell state measurement. After this, A and C are destroyed, meaning their specific states are gone. But the information from C's state doesn't vanish. Instead, it's transferred instantly to B, which could be light years away. Let's pause there. Nothing moved, and yet the state of C appeared on B. The quantum information has been teleported through entanglement and classical communication. That's key. The process still needs some normal info to be sent via regular means to complete the state transfer. But the quantum part, that jumps instantly. Einstein wasn't a fan. He called this kind of thing spooky action at a distance. But experiments have proven it works. We've teleported photons, ions, and even bits of information over 100 kilometers of fiber. In 2017, China's Messias satellite achieved quantum teleportation from Earth to space. But don't get too excited. We're not teleporting people. What's really moving is quantum information, the pattern, the identity, not the object. It's like copying the exact configuration of a molecule and pasting it somewhere else. Except you didn't send the molecule, just its essence, reconstructed from scratch. Why does this matter? Because in the world of quantum computing and cryptography, quantum teleportation is how secure information could be transmitted, unhackable by classical methods. It's also how quantum networks, the so-called quantum internet, might be built, linking quantum computers through entangled connections rather than cables or radio. And here's a wild twist. The original particle loses its state during the process. So in a way, the original is gone and only the copy exists. It's not duplication, it's transfer, like a cosmic delete and paste. This raises questions that go way beyond physics. What does it mean for identity? What if consciousness worked like this, not in practice, but in concept? Is there a deeper layer of reality that entanglement is just barely exposing? You start to wonder, if teleportation of quantum information is possible, what else is? Spooky action at a distance. Einstein hated it. He even called it spooky action at a distance. Yet this strange phenomenon might be one of the most mind-bending aspects of quantum entanglement. Let's say you have two particles, call them particle A and particle B. They're entangled. This means, no matter how far apart they are, they're still mysteriously connected. If you do something to particle A, particle B responds instantly, not after a delay. Instantly. Here's the weird part. It doesn't matter if they're across the room or across the galaxy. Imagine flipping a coin. Normally it lands either heads or tails randomly. But with entangled particles, if particle A is heads, particle B is guaranteed to be tails, and vice versa. That's not the strange part. The strange part is that you don't even know what particle A is until you check it. And the moment you do, particle B chooses its state at the same time, even if it's millions of light years away. This seems to break one of the most sacred laws in physics, the speed of light. Nothing should be able to send a signal faster than that, but entanglement doesn't seem to care. Here's a way to visualize it. Think of a pair of gloves. One is left-handed, the other is right-handed. You put them in two boxes, separate them, and ship one to Mars. You open the box here on Earth and find the left glove. Instantly, you know the one on Mars is right-handed. That sounds simple, but in the quantum world, it's not so straightforward. See, quantum particles don't have a set state like a glove does. They exist in a superposition, meaning they're both left and right until you look. Only when you observe one does it snap into reality. And so does its partner at the exact same time. Einstein, Podolsky, and Rosen challenged this with what's now called the EPR paradox. They argued that there must be hidden variables we don't understand yet, some kind of information that determines the outcome ahead of time, even if we can't see it. But then Bell's theorem happened. Experiments started proving that these hidden variables don't exist. The universe somehow is non-local. That means the behavior of one particle isn't just linked to its own past, but to what's happening far away, right now. It's not about sending signals. It's deeper than that. It's like the two particles are part of a single system, one that stretches across space. Distance doesn't matter anymore. The rules we thought applied to separate objects just don't apply here. This doesn't mean we can use entanglement to send messages instantly, not yet at least. But it does mean that the fabric of reality isn't as local and separate as it seems. Something deeper connects things, something beyond classical physics. Some physicists suggest that space itself might emerge from entanglement, that the reason things feel far away is just a side effect of how entangled the universe is. If that's true, distance isn't even real in the way we think. And that spooky action might just be a glimpse of something far more profound. And here's the twist. We still don't fully understand how or why it works. But every experiment confirms it. Quantum mechanics keeps being right, even when it feels completely wrong. And this is only the beginning. The quantum Zeno effect. You'd think just watching something doesn't change it, right? In the classical world, it doesn't. You can stare at your toaster all you want, and it won't behave differently. But in the quantum world, even watching, just measuring, changes everything. That's where the quantum Zeno effect comes in. It's named after Zeno's paradoxes, the idea that motion can be broken down into so many steps that it seems impossible to move at all. This quantum version plays with time, observation, and the illusion of stillness. Here's the weird part. When you observe a quantum system constantly, you can stop it from changing. You freeze it, not by force, but by attention. Imagine you have a particle in a state where it's likely to change. Maybe it wants to decay or flip from one state to another. But if you keep measuring it again and again and again in tiny intervals, something bizarre happens. It just doesn't move. It stays stuck in that original state. It's like the particle says, I was going to do something, but you keep looking at me, so never mind. This isn't just theory. It's been demonstrated in experiments. Let's say you have an unstable atom ready to decay. Normally, over time, it does just that. But if you keep checking whether it has decayed, constantly measuring it, you can actually prevent it from decaying at all. The act of observing resets its internal quantum clock over and over again. So, what's going on here? In quantum mechanics, a system evolves probabilistically, meaning over time, there's a growing chance it'll change its state. But when you measure it, you collapse that evolving state back into a definite one. Do that too often, and it never gets the chance to evolve at all. It's like trying to fall asleep while someone pokes you every 10 seconds asking, "Are you asleep yet?" You never get there. Now, this might sound like magic or science fiction, but it's a subtle consequence of how time and measurement interact in the quantum world. Here's the kicker. The more often you measure, the less likely the system is to change. That's the quantum Zeno effect. It leads to all kinds of strange possibilities. In theory, it could be used to preserve fragile quantum states for longer, like keeping a quantum computer's qubits from decohering. Just keep checking in tiny intervals and you slow their breakdown. But even more mind-bending? Some have wondered if consciousness itself could trigger a kind of Zeno-like freeze. If observing changes reality, then what happens if you're always observing? Could this be why certain things never seem to change while others collapse instantly? It also raises deeper questions. What does it really mean to observe something? Is it just interaction? Is it a measurement device? Or could it involve awareness? The quantum Zeno effect invites us to rethink the flow of time itself. If watching can freeze motion, then maybe time isn't as smooth and continuous as we believe. Maybe it's more like a strobe light, flickering moments strung together, held in place by consciousness. And then there's its opposite, the anti-Zeno effect. If you observe the system at just the wrong intervals, you can actually speed up its decay. Watching too little, and it slips away faster. It's all about timing. Measurement becomes a kind of dance. Too often, and you paralyze it. Too rarely, and it flies away. Quantum mechanics never fails to take something simple, like watching, and turn it into something reality-shattering. So next time you stare at a clock and it feels like time is frozen, maybe it is. And maybe, just maybe, that's the quantum Zeno effect whispering behind the scenes. Delayed choice entanglement, swapping. So here's something that'll twist your brain. Delayed choice entanglement swapping. Sounds like a mess of words, but stick with me, because what it suggests is time might not work the way we think it does. In regular quantum entanglement, two particles are linked. Measure one, and you instantly know the other. Simple enough, well, as simple as quantum gets. But what if you could take two particles that were never entangled, and then after you've already measured them, decide to entangle them? Yeah. That's what delayed choice entanglement swapping claims to do. Here's how the setup looks. You start with two entangled pairs. Let's call them AB and CD. A and B are entangled. C and D are entangled. You then send A and D to two distant detectors. They're measured independently. No big deal. But now comes the weird part. You take B and C and perform a joint measurement on them, a special kind called a Bell state measurement. This has the power to entangle B and C. But wait, didn't A and D already get measured? Weren't those outcomes already fixed? And yet, once you do that Bell state measurement on B and C, the data from A and D suddenly starts behaving as if they were entangled, even though they were never part of the same pair. Even weirder, the decision to entangle B and C can be made after A and D have been measured, meaning the choice in the present is seemingly changing the outcome of the past. But physicists don't like to say that. Instead, they say there is no definite outcome until everything is put together. In quantum terms, the information is non-local. It doesn't care about time or distance the way we do. Now, this doesn't mean you can go back and change history. You're not rewriting the past, but it does mean the quantum world doesn't treat time in a straight line. It's like the entire setup, past, present, and future, is just one big tangle. You only get the full picture once you look at it all together. This raises some huge questions. Is time itself just a convenient illusion for beings like us who can't see the whole pattern? Are cause and effect just artifacts of the limited way we process information? And it's not just theory. These delayed choice experiments have been done in labs over and over, and they keep confirming this strange idea. The quantum world doesn't follow the rules we think it should. So, next time you're stuck thinking about cause and effect, just remember, on the quantum level, it might not even be a one-way street. The delayed choice quantum eraser. They ran the experiment backward in time, or at least that's what it felt like. It's called the delayed choice quantum eraser, and it flips everything we thought we knew about cause and effect. The idea is deceptively simple, but the implications are unsettling. A decision made in the present seems to reach into the past and change what already happened. Here's how it works. Start with a classic double-slit experiment. You shoot a photon at a screen with two slits, and if you don't look at which slit it goes through, the photon behaves like a wave. It interferes with itself, like it went through both slits at once. But if you do observe the path, if you mark which slit it went through, the interference disappears. The photon acts like a particle and chooses one path. Now here's where it gets strange. Physicists John Wheeler and later Yoon-Ho Kim designed an experiment where you delay the choice to observe the photon's path until after the photon has already passed through the slits. You split the original photon into entangled twins. One twin goes directly to a detector, the other takes a detour, and along this longer path, you get to decide whether to keep or erase the which path information. The detectors that catch the photons record whether or not they interfere, but that outcome depends on a decision made after the photon passed through the slits. It's like the universe is waiting to see what you'll do before it decides what it already did. And no, this isn't just some metaphor. The results are repeatable. The interference pattern appears only when the which path info is erased, even though that erasure happens after the event that supposedly caused the pattern. So what does this mean? Some physicists say it's evidence that the quantum world doesn't care about time the way we do. Cause and effect might not flow in one direction. Others say the act of measurement doesn't just observe the world, it defines it, regardless of when it happens. The delayed choice quantum eraser suggests that what we do now can change what the universe remembers about the past. The effect and the cause might be more deeply entangled than we ever thought possible. The GHZ Paradox. When three particles are entangled in a Greenberger-Horn-Zeilinger GHZ state, something deeply unsettling happens to our idea of reality. Let's say we have three photons, let's call them A, B, and C. These photons are entangled in such a way that, no matter how far apart they are, measurements made on any two of them can instantly tell you what the third one will do. Now here's where it breaks your brain. In the GHZ setup, you can choose to measure the polarization of each photon in different directions. And when you do, you'll get results that perfectly correlate in ways that no classical explanation can reproduce. But here's the twist. When you try to assume the photons had a real state all along, hidden from us, like little instructions coded into each one, it leads to a contradiction. You literally can't assign values to all their properties in a way that matches the observed outcomes. In other words, if you're trying to believe these particles just had some preset plan they were following. The GHZ experiment blows that idea apart. Unlike Bell's theorem, which relies on statistics, the GHZ paradox doesn't. It gives you a full-on logical contradiction with just a few simple steps. It's like the universe saying, "I dare you to make sense of this." What makes it worse, or more beautiful depending on your perspective, is that GHZ doesn't need loopholes or uncertainty. It's not about probability anymore. It's pure logic. If realism and locality were both true, you should get one result, but you always get another. So either the world isn't local, or it isn't real. This is why the GHZ paradox has become one of the sharpest tools we have to poke holes in our everyday assumptions about the world. Because when three tiny photons, separated by miles, act like a single indivisible system, it tells us that quantum entanglement isn't just weird, it's fundamental. It's not just about particles, it's about the rules of the universe itself. Hardy's paradox. In classical logic, if two things can't both be true and can't both be false, then one must be true and the other false. But Hardy's paradox throws that entire rulebook out the window. Picture two particles, an electron and a positron. They travel toward overlapping interferometers, setups that split and recombine particles' paths. If both take the dangerous paths, the ones that cross, they annihilate. But here's the catch. Sometimes detectors fire as if both particles took those paths. Without annihilation. That's not supposed to happen. They should destroy each other. What's even weirder is this. Each particle seems to know what path the other took. Without directly interacting, the experiment shows outcomes where, logically, one particle can't exist without the other also existing in a forbidden path. And yet, we detect both. No classical explanation works. You can't say, maybe they just took different routes, because the detections don't add up. You can't say, well, maybe they weren't really there at the same time, because the setup ensures simultaneity. It's like watching two people run straight toward each other and pass through without collision, while also leaving footprints proving they both took the exact same path. Hardy's paradox challenges not just locality, but realism. It tells us quantum particles don't follow paths the way we think. They aren't real in the classical sense until they're observed. And when we do observe them, they appear to have done the impossible. And if that doesn't make your brain feel like it's being untangled, the twist is this. The paradox doesn't even require entanglement in the traditional sense. It uses pure quantum logic, superpositions, and measurement collapse to create something that shouldn't exist. It's like quantum mechanics is reminding us the rules don't bend, they vanish entirely. The GHZ state triplet spookiness. There's something strange about three particles being entangled at once, not just two, like in the usual quantum experiments, but three linked together in a way that breaks classical intuition even further. This is where the GHZ state, or Greenberger-Horn-Zeilinger state, comes in. In this quantum configuration, we're no longer talking about just spooky action at a distance between two partners. We're dealing with a triplet, three particles sharing a quantum state so deeply that measuring one instantly determines the state of the other two, no matter how far apart they are. Here's what makes GHZ so wild. It's not just about correlations anymore, it's about contradictions. In the classic GHZ experiment, physicists set up three entangled particles, each heading to a separate detector. Then, they measure a specific property, usually spin, along chosen axes. According to quantum mechanics, the outcomes follow a strange set of rules that always seem to agree, until you try to explain them with local realism. That's the kicker. Classical physics says each particle should have its own local values predetermined before measurement. But GHZ states blow this idea apart. There's no way to assign local variables that can explain all the results, not even probabilistically. This isn't just violating a Bell inequality, it's showing that even the logic behind those inequalities collapses when faced with three entangled particles. The math says these results must always add up to an even number. But reality, when tested, sometimes gives an odd one. It's not a statistical fluke. It's a full-blown logical contradiction between the predictions of quantum mechanics and what classical reasoning demands. So what does this mean? It means nature doesn't just prefer weirdness, it requires it. The GHZ experiment proves that particles don't have properties until we look. And even more disturbing, their properties aren't even real in the way we think about reality. The outcomes don't depend on individual particles, but on the whole system, measured all at once. Three particles, one wave function, zero classical explanation. Quantum entanglement wasn't meant to make sense, but with the GHZ state, it doesn't just confuse, it defies logic itself. Entanglement in many worlds interpretation. You've probably heard people say, in another universe, there's a version of you doing something completely different. It sounds like science fiction, but in quantum physics, the many worlds interpretation takes that idea seriously, and entanglement plays a central role in it. In this view, every time a quantum event occurs, reality branches. When two entangled particles are measured, their outcomes aren't randomly decided in some spooky, faster-than-light way. Instead, the universe splits. In one branch, particle A is spin up and particle B is spin down. In another, it's the reverse. No signal travels between them. There's no need. The branching handles it all. This interpretation was proposed by Hugh Everett in 1957. He wanted to solve the measurement problem, why observing a quantum system seems to collapse its wave function. His idea, the wave function doesn't collapse. It continues evolving, and observers simply split into copies that experience different outcomes. So, how does entanglement fit in? Let's say you and your friend each take one half of an entangled pair. You go light years apart. Then you measure your particle. Instantly you know what your friend's result will be. In traditional interpretations, this feels spooky. But in many worlds, both outcomes happen. The universe branches, and each of you finds yourselves in the version where the measurement matches. There's no communication between particles. Instead, the entangled system and the observers evolve into a superposition of different realities, each consistent with the rules of quantum mechanics. It's weird, but it's consistent, and it removes the mystery of how entanglement seems to work faster than light, because it doesn't. There's just more universes than we see. Here's where it gets trippy. In this view, your entire life is constantly branching. Every decision, every quantum event splits the universe. Entanglement doesn't just link particles, it links realities. Now imagine this. If entangled particles are constantly branching realities and you're made of particles, how many versions of you are out there, and what are they doing right now? Want to go deeper? Wait until you hear how some physicists think quantum computers might exploit these parallel worlds. But that's coming in the next segment. Quantum decoherence, the bridge between quantum and classical. I used to think quantum mechanics was just about tiny particles doing weird things. But then I stumbled onto something that changed the way I understood the world. Quantum decoherence. It sounds technical, but it's actually one of the most important keys to understanding why the quantum world looks so different from our everyday experience. Here's the idea. At the quantum level, particles exist in a superposition, meaning they can be in multiple states at once. A photon could be traveling two paths at the same time. An electron could spin in two directions at once. It's only when we measure or interact with them that we see just one outcome. But why? Why don't we see those strange, overlapping states in our daily lives? This is where decoherence comes in. Decoherence is what happens when a quantum system interacts with its surrounding environment. It doesn't mean the system is destroyed. It doesn't even require a human observer. Just interacting with light, air, or even other particles can cause a quantum system to lose its delicate superposition. Think of it like this. Imagine a violin string vibrating in perfect silence. You can hear every subtle nuance, every wave. That's a quantum system in isolation. But now imagine someone turns on a fan, a dog starts barking, and the street outside gets noisy. You can't hear the violin anymore. The vibration is still there, but it's buried in the noise. That's decoherence. The quantum information gets lost, not destroyed but smeared out into the environment. That's why you don't see your coffee mug in two places at once, or your cat both alive and dead. The atoms in everyday objects interact constantly with their surroundings, forcing them into one definite state. The weirdness of quantum mechanics fades into the classical world we experience. But there's something even deeper. Decoherence doesn't explain why a specific outcome happens. It just explains why the other possibilities vanish so quickly that we never see them. It bridges the gap between quantum theory and classical reality, but leaves the ultimate mystery of measurement untouched. Still, it helps make sense of so many things, like why entanglement is so fragile in real-world systems, or why quantum computers are so hard to build. Even the tiniest disturbance, heat, motion, light, can collapse the delicate web of quantum information. It's not that the quantum world is far away or unreachable, it's all around us. But the reason we don't see it? Decoherence. It's like a fog that turns possibility into certainty before we even notice. And that's what makes this topic so strangely comforting. Because the universe isn't hiding its secrets from us, it's whispering them constantly in the quiet, fleeting moments before everything collapses into the ordinary. The quantum Zeno paradox. Every time you look, it freezes. That's the strange logic behind the quantum Zeno effect, a phenomenon where watching a particle closely enough can actually stop it from changing. In classical physics, observation is passive. A rock doesn't care if you're looking at it. But in the quantum world, observation means interaction. It changes everything. Let's say a quantum particle is in a superposition, like being in two places at once. If left alone, it will eventually shift into one defined state. But what if you keep measuring it over and over? It resets each time, forced back into the same state, as if time has barely moved. It's like trying to let a candle melt, but someone keeps lighting a new one every second. In real-world terms, this is more than a thought experiment. Scientists have actually frozen the decay of unstable atoms by observing them continuously. The particle wants to evolve, but our interference traps it in place. This has implications for quantum computing, nuclear physics, and even time perception itself. It's a reminder that in quantum mechanics, the line between observer and participant doesn't just blur, it disappears completely. Watch too closely, and nothing moves. The No-Communication Theorem. No matter how strange entangled particles behave, there's one thing you can't do with them: send information faster than light. That's where the No-Communication Theorem comes in. Let's say you have two entangled particles. One is with you, the other is light years away with your friend. Now, if you measure your particle and it instantly collapses the state of your friend's particle, does that mean you've sent information faster than light? Nope. Because even though the particles are linked, the outcome of your measurement is random. You can't control what result you'll get, and because your friend's particle also ends up random, though correlated, there's no usable message being sent. It's like flipping a coin and someone else's coin far away, always landing the same way. But neither of you can choose heads or tails. You both just get the same random result. That's not communication, that's coincidence at a quantum level. This idea protects Einstein's theory of relativity. Nothing, no information, no signal, breaks the speed of light barrier. Quantum physics might look spooky, but it doesn't let you cheat causality. So even with all its weirdness, entanglement still respects one fundamental rule of the universe: no message, no influence, can travel faster than light. Still, the mystery remains. If no information is traveling, then how do the particles know how to stay perfectly matched? That's the real puzzle. Delayed choice quantum eraser. You'd think that once an event has happened, it's done, carved in the stone of time. But quantum mechanics loves to mess with that idea. In 1999, physicists carried out an experiment called the Delayed Choice Quantum Eraser, which basically asked, can the future change the past? Sounds ridiculous, right? But stay with me. Here's what they did. They shot single photons, tiny particles of light, through a double-slit setup. If you're familiar, this setup can show either a wave pattern, if you don't observe the path, or two bands, if you do observe which slit the photon went through. The weirdness starts when they add something called a quantum eraser. After the photon goes through the slits, but before it hits the detector, they have the option to erase the witch path information, meaning they can choose not to know which slit the photon went through. Here's the catch. The decision to erase or not is made after the photon has passed the slits. And yet, depending on that choice, the photon behaves as if it already knew what would be decided in the future. If the witch path information is erased, the interference pattern appears. If it's kept, no interference. So what's going on here? One interpretation is that reality isn't finalized until it's observed, and that includes the past. The photon doesn't decide what it did until someone looks. In other words, the act of measurement retroactively determines the outcome. This doesn't mean you can go back in time and rewrite history, but it does mean that at the quantum level, time isn't as one-directional or fixed as we like to believe. Reality might not be a neatly ordered sequence. It might be more like a flexible script, one that only gets finalized when you press play. If that doesn't make your brain feel like a pretzel, wait until you hear what the next experiment suggests. Quantum entanglement and black holes. The ER =EPR conjecture. There's a theory so strange, so mind-twisting, that it suggests black holes and entangled particles might be two sides of the same coin. Let's start with the problem. Quantum entanglement says two particles can be instantly connected no matter how far apart they are. But in general relativity, space and time are woven together by gravity. And black holes? They are the most extreme examples of warped spacetime. Physicists Juan Maldacena and Leonard Susskind proposed something wild. They called it ER =EPR. On one side, you have ER, which stands for Einstein-Rosen bridges, more commonly known as wormholes. On the other side, EPR refers to Einstein, Podolsky, and Rosen's paradox on quantum entanglement. ER =EPR suggests that every pair of entangled particles is actually connected by a microscopic wormhole, a bridge through spacetime. Let that sit for a moment. This means the mysterious connection between entangled particles might not be spooky action at a distance after all. Instead, it could be an actual bridge, a tiny shortcut in the fabric of reality. Now think about what that implies. If you entangle two particles and separate them by light years, there might be a hidden tunnel between them. Not something you could travel through, not in the usual sense, but a link that bends the rules of distance just enough to keep their states perfectly aligned. And here's where it gets deeper. Black holes are known to emit Hawking radiation, slowly losing mass over time. If a black hole emits entangled particles and one escapes while the other stays inside, then over time, the radiation could tell you something about what's inside the black hole. But wait, that breaks the rules of physics. The No-Cloning Theorem says information can't be copied. The black hole information paradox says information going into a black hole can't just disappear. So how does it all make sense? ER=EPR might be the answer. What if the inside of the black hole and the radiation outside are still connected by entanglement? What if that connection is actually a wormhole? Suddenly, black holes aren't information destroyers. They're gateways. They're holding on to the other half of the story. And if ER=EPR is true, it's not just black holes. Everything that's entangled might be subtly stitched together by spacetime itself. So here's the thought that might follow you into dreams. Every pair of entangled particles might be whispering through tiny tunnels in space. The more you look at it, the less space means what you think it does. The universe may not be a vast empty stage. It may be a web of invisible connections. And somewhere between gravity and quantum mechanics, the secret language of the universe is quietly unfolding. Quantum entanglement and the cosmic microwave background. When you look at the sky through a powerful telescope, you're not just seeing stars. You're seeing the oldest light in the universe, the cosmic microwave background, or CMB. This faint glow is the leftover radiation from the Big Bang, and it's been traveling across the universe for over 13 billion years. But here's what's strange. Hidden in this ancient light might be evidence of quantum entanglement on a cosmic scale. The idea sounds unbelievable. Entanglement usually happens with particles at subatomic levels, photons, electrons, atoms. But what if, in the first moments of the universe, entire regions of space became entangled? As the universe expanded, those connections would have stretched out with it. Today they'd be light years apart, yet still mysteriously linked. Some physicists believe they've seen hints of this in the CMB's tiny temperature fluctuations. These fluctuations aren't random. Patterns repeat in ways we can't fully explain, unless entanglement had a role in shaping them. In other words, the structure of the universe itself might carry the fingerprint of quantum weirdness. And it raises a big question. If quantum entanglement helped shape the early universe, is it still shaping it now? Could dark energy or dark matter be the result of hidden entangled fields we don't yet understand? We're just scratching the surface, and this idea alone could rewrite everything we think we know about how reality works. The holographic universe and entangled boundaries. What if everything around you, your body, your room, your entire life, isn't truly three-dimensional at all, but the illusion of a deeper two-dimensional reality? This isn't science fiction. It's called the holographic principle, and it's one of the strangest yet most powerful ideas in theoretical physics. And when you mix it with quantum entanglement, something even weirder starts to emerge, something that could redefine what space, time, and even existence really are. Let's start with black holes. Physicists noticed something odd about them decades ago. The amount of information, or entropy, inside a black hole wasn't determined by its volume, like you'd expect. It was determined by its surface area. Imagine cramming 1,000 books into a box. Normally, you'd think the more space inside the box, the more you can fit. But with a black hole, it's like the number of books depends only on how much paper you glued to the outside. This strange rule suggested something wild, that the information inside a black hole could actually be stored on its boundary, the event horizon, like a giant cosmic hard drive. Then came the kicker. What if the entire universe worked this way? This led to the holographic universe hypothesis, the idea that everything we experience as real might actually be a projection of information encoded on a distant boundary of the cosmos. In other words, your entire 3D world could be just a hologram. Sounds crazy, right? But here's where quantum entanglement comes in. In 2014, theoretical physicists started noticing something fascinating. When they tried to describe a holographic universe mathematically, especially in simulations using something called the AD-CFT correspondence, a pattern emerged. Entanglement wasn't just a side effect of the universe. It was its foundation. They realized that if you tried to reduce entanglement in these models, space-time itself began to fall apart. Without entanglement, the fabric of the universe disintegrated. Connections between particles weren't just weird tricks, they were the glue that held reality together. Think about that. It's not that entanglement happens inside space, it's that space happens because of entanglement. Let that settle in. This leads us to a shocking idea. The boundaries of the universe, the edges where information is encoded, are all entangled. And that entanglement projects our reality into being. You're not just in the hologram, you're made of it. So what happens at those boundaries? If the edges of the universe are entangled, then any change at one boundary might instantly affect distant parts of the cosmos, not because something is traveling through space, but because the entire structure is fundamentally connected, like shaking one corner of a spider's web and watching the whole thing quiver. This also has massive implications for black holes. If the inside of a black hole is encoded on its surface, then maybe nothing is ever truly lost. Maybe the information is preserved at the boundary and remains entangled with the rest of the universe. This would solve the black hole information paradox, which has stumped scientists for years. And it doesn't stop there. Some physicists believe that you, right now, might be entangled with regions of space so distant they're beyond the observable universe, that your thoughts, your choices, even your memories, aren't isolated sparks in your brain, but quantum ripples stitched into a vast hidden network at the boundary of existence. It's hard to wrap your head around, because if this is true, then the boundary isn't just a backdrop. It's the source. And quantum entanglement isn't just a curiosity, it's the very scaffolding of space and time. So the next time you look around at your room, your hands, the stars in the sky, ask yourself, what if none of this is really here? What if it's all just the edge? And somewhere far beyond your eyes, the true picture is waiting, written not in atoms, but in entangled light. Entanglement in nature, how plants might use it. Quantum entanglement is often thought of as something that only happens in high-tech labs or deep within the quantum realm, particles connected in strange ways we can barely detect. But what if this phenomenon isn't just a curiosity of physics? What if nature itself has been using quantum entanglement for billions of years, and we're only just now catching on? Let's talk about plants, more specifically, photosynthesis. Photosynthesis is the process by which plants, algae, and some bacteria capture sunlight and turn it into chemical energy. It sounds simple, but what actually happens inside a leaf is staggeringly complex. Light hits a chlorophyll molecule, exciting an electron, and somehow that energy gets transferred through a maze of protein structures to the reaction center, where it gets stored as usable energy. What's amazing is how efficient this process is. Nearly every bit of energy absorbed by the plant gets used. That kind of efficiency is nearly impossible to replicate in artificial systems. So how do plants pull this off? Here's where it gets mind-blowing. Some scientists believe that quantum entanglement might play a role. In 2007, a team of researchers from Berkeley and the University of Illinois used ultra-fast lasers to observe what happens inside the light-harvesting complex of a photosynthetic organism. What they found shocked them. Instead of energy just hopping randomly from molecule to molecule, like a frog jumping across lily pads, the energy wave seemed to explore all possible paths at once. It behaved like a quantum particle in superposition. Even more fascinating, the energy transfer appeared to remain coherent, meaning it stayed in a quantum state longer than anyone expected. For several hundred femtoseconds, that's a quadrillionth of a second, the energy moved through the complex as if it were part of a delicate quantum dance. During that time, molecules may be operating in a state of entanglement, coordinating their behavior across different regions of the complex, even though they're separated by several nanometers. Now, in human terms, that distance is tiny, but in quantum terms, that's massive. It's like two dancers staying in perfect rhythm even though they're on opposite ends of a football field and there's no music playing. How are they doing it? This is what's led researchers to ask, could quantum entanglement be part of the secret to photosynthesis? To be clear, no one's saying that chlorophyll molecules are conscious or that plants are thinking in quantum terms. But nature doesn't need to know how something works to take advantage of it. Evolution doesn't invent things, it discovers what works and uses it. If entanglement gives photosynthetic systems even a tiny edge in efficiency, that's enough for natural selection to run with it. And it's not just plants. Similar quantum effects might be happening in other biological systems. Take bird navigation. Birds, like the European robin, migrate over thousands of kilometers, guided not just by landmarks or stars, but by the Earth's magnetic field. But here's the catch. Earth's magnetic field is extremely weak. So how do birds detect it so precisely? One leading theory involves a protein called cryptochrome, found in birds' eyes. When light hits cryptochrome, it creates a pair of entangled electrons. The theory goes that the angle of Earth's magnetic field influences how long this entanglement lasts, giving the bird a kind of internal compass. In other words, the bird might see the magnetic field through a quantum process. Back to plants. If quantum entanglement is happening inside their leaves, what does that mean for us? First, it's a humbling reminder that nature has been running complex quantum experiments long before we built labs and colliders. Second, it challenges the idea that the quantum world is fragile or only works in sterile conditions. Plants are messy, leaves are full of noise, heat, vibrations, chaos. And yet, quantum coherence appears to survive, even thrive. This opens up big questions. Could other biological systems be tapping into quantum entanglement? Could fungi, which form vast underground networks, be using entangled signals to transfer information? Could the human brain have quantum processes we don't yet understand? It also offers inspiration. If plants can do quantum computing with chlorophyll, maybe we can learn from them. Already, researchers are designing solar panels and energy systems modeled on photosynthesis. If we figure out how to mimic the quantum tricks plants use, we might unlock breakthroughs in efficiency, energy storage, and even computing. There's still a lot we don't know. Quantum biology is a young field, and many of these ideas are still hotly debated. But the possibility that life itself is quantum entangled, that's not just a cool theory. It's a complete shift in how we see the world. It means the boundaries between physics and biology aren't as solid as we thought. It means the weirdness of quantum mechanics might not just be confined to atoms and particles, but might be woven into the fabric of life itself. And if that's true, then maybe every time you take a walk in the forest, every leaf you see is quietly performing a kind of quantum magic, not with fanfare or lasers, but with elegance, precision, and a level of intelligence we're only beginning to understand. Quantum gravity and the entangled fabric of spacetime. Quantum gravity. The phrase alone sounds like something plucked straight from a science fiction novel, but it's one of the most pressing mysteries in physics today. You see, on one hand, we have quantum mechanics, a theory that rules the world of the tiny, where particles can be in multiple places at once and teleport their properties across space. On the other, we have Einstein's general relativity, which explains how gravity warps the fabric of space and time. The problem? These two theories don't get along. They speak entirely different languages. And nowhere is this conflict more apparent than when we ask, what is the true nature of space-time? At the center of this mystery is an idea that might surprise you: entanglement. That strange quantum connection where two particles, no matter how far apart, behave like they're sharing information instantaneously. What if space-time itself, the very thing we think of as the background of the universe, emerges from entanglement? This is where things start to bend your brain. Physicist Mark van Ramsdonk introduced a provocative idea. If you take two quantum systems that are not entangled, the geometry between them is disconnected, like two islands in an infinite void. But when those systems become entangled, a bridge called a wormhole, or Einstein-Rosen bridge, forms between them. Not a literal tunnel you could crawl through yet, but a mathematical connection that glues space together. In this view, entanglement is the thread that weaves space-time into existence. Without entanglement, space as we know it might not even exist. So instead of thinking of space as a stage where particles dance, space is what emerges when enough particles are entangled. But it goes deeper. In AD-CFT correspondence, a famous duality proposed by Juan Maldacena, entanglement becomes the tool for stitching together higher dimensional space. This holographic model suggests our universe might work like a 3D hologram projected from a 2D surface. Imagine a vast cosmic screen at the edge of the universe. Everything happening here, including space-time, gravity, and even your thoughts, is encoded on that 2D boundary. And what controls the shape and behavior of space-time within? The pattern of entanglement on the boundary. Take away the entanglement and the geometry falls apart. Literally. Physicists simulated this idea and showed that reducing entanglement on the boundary causes space to tear apart inside. It's like deleting the pixels of a hologram. You don't just lose details, you lose entire chunks of reality. So what does this mean for gravity? Traditionally, gravity is a force that pulls objects together. But if space-time is built from entanglement, gravity might not be a force at all. It could be an emergent phenomenon, a side effect of how entangled bits of information organize themselves, like how temperature is not a fundamental property, but emerges from the motion of molecules. Gravity might be the result of entangled information trying to reach equilibrium. One experiment hinting at this involves entropic gravity, a controversial but fascinating idea. It suggests that when you move an object closer to a mass, you're actually changing the entropy or information associated with that region of space. This change creates what we interpret as a gravitational pull. It's not a force. It's information trying to balance itself. In this sense, gravity becomes a thermodynamic effect of entanglement. Even black holes, those mysterious cosmic sinkholes, begin to look different. Stephen Hawking once shocked the world by suggesting black holes evaporate over time, leaking radiation that carries away information. This clashed with quantum theory, which says information can't be destroyed. The solution? Entanglement again. Information might escape a black hole not as raw bits, but as entangled correlations within Hawking radiation. In other words, black holes don't destroy information. They scramble and entangle it. This leads to the famous firewall paradox, which pits quantum theory against general relativity. If entanglement is broken at the event horizon, it leads to a firewall, an energetic wall that burns anything falling in. But if we keep the entanglement, it defies what general relativity predicts. The debate rages on. And yet, the bigger question remains, is space-time just a byproduct of quantum information? New research points to something astonishing. Space-time might not just be built by entanglement, it might be constantly updating in real time, shaped by the shifting entanglement patterns of quantum fields. Every time a quantum interaction occurs, anywhere in the universe, it subtly alters the shape of space itself. Like ripples on a quantum pond, these entanglements cascade, building and bending space-time moment by moment. So where does this leave us? The deeper physicists go into the nature of gravity, black holes, and space-time, the more they bump into entanglement as the hidden architect. It's no longer a quirky side effect of particle physics. It may be the very foundation of reality, not atoms, not energy, but pure information. And perhaps the final irony? We've spent centuries trying to understand gravity as a fundamental force, only to find it might be a shadow cast by the invisible web of entanglement behind everything. The simulation hypothesis meets entanglement. What if everything you've ever seen, touched, or felt wasn't real? What if the entire universe was just code, complex, perfectly calibrated, and running inside some hyper-intelligent simulation? Sounds like sci-fi, right? But here's the strange twist. Quantum entanglement, the same phenomenon that once baffled Einstein, might actually be the glitch in the matrix, the telltale sign that this reality isn't what it seems. Let's rewind. The simulation hypothesis suggests that what we perceive as reality is actually a digital simulation, likely created by an advanced civilization. Now add entanglement into the mix. Two particles, separated by vast distances, can still affect each other instantly. Not through a signal, not through a medium, just boom! One moves, the other knows. The connection is immediate, violating the classical understanding of space and time. Now here's the thing. If we were inside a simulation, then the core rules of the simulation could override the laws of physical distance. Just like in a video game, you can have two characters in different parts of a map, but their data is stored in the same hard drive. Their actions can be linked because the engine that governs the world isn't limited by the same rules the characters perceive. In this view, entanglement isn't some magical quantum trick. It's a clue, a crack in the wall, a function of how the simulated universe processes information. When two particles are entangled, maybe it's because the simulation is running a shared code between them. Their states aren't separate. They're part of one shared line in the cosmic script. And it doesn't stop there. Quantum information theory, something real scientists are diving into, suggests that at the deepest level, our universe might be about bits, not atoms. That is, fundamental reality might be information itself. Binary code, ones and zeros. Logic gates. Think about it. If entanglement is information being shared instantly between particles, doesn't that feel a lot like how data is handled in a computer? Now consider this. Physicists have found that black holes don't just swallow information, they store it on their event horizon. The surface of the black hole contains all the information about what fell inside. It's like a hard disk. Even weirder? The math used to describe the universe's interior can sometimes be rewritten entirely on its boundary. This is called the holographic principle. That sounds suspiciously like a simulation storing data in compressed formats. Think of it as a computer game, rendering only what you see on screen. Why calculate everything else if you're not looking? This means entanglement might be the stitching between those boundaries. The reason two faraway particles remain connected could be because they're actually close to each other in the simulation's source code. From our in-world perspective, they're distant. But from the simulation's architecture, they're side by side. It also explains why entanglement doesn't violate causality or allow faster-than-light communication. The simulation enforces the rules, but it also operates behind the curtain. You can't hack it with a telescope or a rocket ship. You'd need to access the code itself. But entanglement gives us a hint that the code exists. Let's take it at one level deeper. In quantum computing, information can be stored and processed in qubits, which can be entangled. This means a quantum computer can process massive amounts of information at once. But what if our universe is running on a quantum computer itself? Some physicists, like Seth Lloyd, have proposed that the cosmos behaves exactly like one, processing information on the quantum scale, evolving according to algorithms. In this view, quantum entanglement is not just a feature, it's the architecture. Entanglement is how the simulation links events, maintains consistency, and enforces probability. It's the shortcut, the background thread. You don't see it happening, but it's always there, maintaining the illusion of a seamless world. And now, here's where it gets a little uncomfortable. If the universe is a simulation and entanglement is part of its processing system, then we're not just observers, we're part of the code. Our choices, our thoughts, might be emergent behaviors of a more complex script. The universe appears rich and textured because the simulation has layers, nested systems of cause and effect bound together by entangled data streams. But that raises a bigger question. Who or what wrote the code? Is it an alien civilization running ancestor simulations? A post-singularity AI searching for meaning? Or something even more transcendent, something indistinguishable from what we used to call God? We may never know, but every time we observe an entangled particle, every time a quantum system collapses into certainty, it's as if the simulation flickers just for a moment, revealing its presence. Entanglement is the glitch, the whisper from the back end. It's the nudge that says, this isn't all there is. And once you've seen it, you can't unsee it. What if love is quantum, the softest theory of them all? There's a quiet theory whispered between physicists and poets alike. A theory so gentle, so human, it almost seems too tender to belong among the hard edges of quantum mechanics. But here it is. What if love itself, this deep, unexplainable bond between two people, is not just a chemical reaction, not just a biological drive, but something quantum? What if love is a form of entanglement? In the quantum world, particles can become entangled, so deeply connected that no matter how far apart they are, the state of one instantly affects the other. Einstein called it spooky action at a distance, but spooky might just be another word for mysterious, magical, or even romantic. Let's start with this question. Have you ever thought about someone right before they texted you? Or felt a sudden wave of sadness only to find out later that someone close to you was going through something heavy at that exact moment? Sure, skeptics would call it coincidence. But the deeper we dive into the science of entanglement, the more that word loses its grip. Quantum entanglement has been proven again and again. We've seen photons behave in lockstep across vast distances. We've seen particles feel each other's state, change instantly, with no signal sent, no delay. It defies our classical understanding of space and time. But if subatomic particles can be this connected, why not us? Now imagine two people. Maybe they met by chance, or maybe something bigger brought them together. Over time, they build memories, exchange words, share touch, glance, silence. They synchronize heartbeats, complete each other's thoughts, finish sentences without trying. They move together like an invisible thread is pulling them into the same rhythm. Isn't this its own kind of entanglement? Some researchers have explored this idea through biofield science and heart-mind coherence, hinting that the electromagnetic fields generated by our hearts and brains may interact in ways science hasn't fully mapped. And when two people spend enough time together, their rhythms align, not just emotionally but physically. Their heart rates sync, their brainwaves find similar patterns. It's measurable. But is it just biology, or is there something else? Let's take it a step deeper. Quantum entanglement isn't limited to time or space. It can be preserved even after entangled particles are separated by miles. So when you meet someone who feels like you've known them forever, could it be that your connection already existed in some deeper layer of reality? Could love be a kind of quantum memory, a resonance from beyond this timeline? This would mean that when we fall in love, We're not just reacting to looks, voice, or scent. We're recognizing something our conscious mind can't name, but our quantum body remembers. Like two particles that once spun together in the same direction, then were flung apart, only to find each other again. Now let's go even softer. Quantum mechanics tells us that the observer changes the observed, that simply looking at a particle changes its behavior. If love is quantum, then when we truly see someone, not just with our eyes, but with intention, compassion, attention, we are literally shaping who they become, and they are shaping us. In every word, every glance, we collapse potential into reality. Love, then, is not a passive feeling. It's an active participation in another person's becoming. Entanglement also survives chaos. Even in noisy environments, the quantum link persists. This might explain why some relationships endure even after time, distance, and struggle. The entanglement doesn't vanish just because communication breaks down. It's still there, silent, humming, waiting. And just like quantum systems, love isn't deterministic. It doesn't follow a script. It's probabilistic, uncertain. That's why it feels so risky and so alive. The more you try to pin it down, the more it slips through your fingers. But when you surrender to its uncertainty, something extraordinary happens. You begin to trust the dance, the shared unfolding. There's also something to be said about coherence. In quantum physics, coherence means that a system is in perfect harmony, with all its parts aligned. The more coherence in an entangled system, the stronger its connection. Could the same be true of us? The more we bring our true self into a relationship, our honesty, presence, vulnerability, the stronger our bond becomes. And perhaps this is why real love can't be forced. Just like entanglement, it emerges naturally, unpredictably. You can't manufacture it. You can only notice it when it appears. You can only honor it, nurture it, protect it. Skeptics might say this is all metaphor. But maybe metaphors are the bridge between science and the soul. Maybe we're only now beginning to find language for truths we've always felt. After all, if entangled particles defy time and space, maybe love does too. Maybe when someone passes away and we still feel them, dream of them, hear their voice in moments of silence, it's not just grief. Maybe the entanglement hasn't broken. Maybe it never will. So what if love is quantum? Maybe it always was. And maybe, just maybe, that's why it feels like magic. Quantum biology, how life itself might be quantum. When we think about quantum physics, we usually picture tiny particles doing strange things, teleporting, entangling, or existing in multiple places at once. But what if I told you that this isn't limited to distant particles in labs or the edges of the universe? What if quantum mechanics is happening right inside of you, right now? Welcome to quantum biology, the idea that life itself depends on quantum effects. For decades, biology and quantum physics were treated like strangers. Biologists dealt with cells, genes, and molecules, while physicists played with probabilities and wave functions. But the line between them is starting to dissolve, and where they meet is where the magic begins. Let's start with something simple, but mind-blowing: photosynthesis. You've probably heard that plants take sunlight and turn it into energy, but how they do this efficiently, so efficiently that no human-made solar panel can compete, was a mystery for a long time. Then scientists looked closer and discovered something weird. When a photon of light hits a plant's chlorophyll, it needs to travel to a reaction center to kickstart energy production. But this journey isn't random. The photon doesn't try every path and hope for the best. Instead, it seems to try all possible paths at once, like a quantum wave exploring multiple routes, then collapsing into the most efficient one. This is a quantum effect called superposition, and plants might be using it every day, every moment, to stay alive. It's like the plant is letting nature calculate the best route using quantum logic. Imagine Google Maps, but powered by quantum waves instead of code. This isn't just theoretical. Experiments show real signs of quantum coherence in photosynthesis. That means the parts of the plant doing this are behaving like a tiny quantum computer. That's life, using quantum mechanics. But let's go even deeper. Birds like the European robin migrate across vast distances, somehow knowing where north is, even when the sky is cloudy and there are no visible cues. For a long time, this was a mystery. How could they see magnetic fields? It turns out their eyes may contain special proteins called cryptochromes. These proteins hold electrons that get excited by light and then become entangled. While entangled, their quantum state is sensitive to Earth's magnetic field. As the bird moves, the angle of magnetic influence shifts, changing how the entangled electrons behave, possibly creating a visual pattern the bird can perceive. In other words, birds may literally see magnetic fields using quantum entanglement in their eyes. We always thought nature was too messy, too warm, too noisy for delicate quantum effects to survive. After all, quantum stuff usually happens in isolated, ultra-cold labs. But maybe life found a way to protect these quantum secrets in the chaos of the body. Let's not forget our own noses. Smell has always been explained by molecular shapes fitting into receptors, like keys into locks. But that idea doesn't fully explain why some molecules with identical shapes can smell completely different. Enter a new theory, quantum tunneling. It suggests that smell receptors might detect not just shape, but the vibration of molecules. That's right, quantum-level vibrations. Electrons in your nose could be tunneling through a molecule, sensing its signature frequency like a musical note. You're not just smelling a shape, you might be sensing quantum vibrations, and that's not all. Some researchers think that enzymes, those little machines in your cells that build and break things, also use quantum tunneling to speed up reactions. Instead of waiting for atoms to bump into the right place, electrons might tunnel instantly across barriers. It's like teleportation, but for chemistry, and it might be essential to how life works. All of this leads us to a much deeper question. What if quantum biology isn't just about birds or plants or enzymes? What if consciousness itself, our thoughts, our awareness, is also quantum? Some theories suggest the brain might use quantum coherence in microtubules, tiny structures inside neurons. While controversial, it opens the door to a radical idea that conscious experience might arise from quantum information processing, something beyond classical physics. Could our awareness, our thoughts, dreams, and sense of self, be tapping into the same strangeness that governs particles? Could life be a quantum phenomenon? We still don't have all the answers, but the more we look, the more nature seems to whisper, "I've been quantum all along." And if that's true, then we are walking, breathing, thinking examples of the universe's strangest laws, carried not just in the stars, but in every leaf, every wing, every heartbeat. Quantum tunneling, slipping through walls of reality. Let's say you throw a tennis ball at a wall. You'd expect it to bounce back, right? That's how the world works, at least the world we can see. But shrink things down to the size of atoms, and suddenly, that wall isn't as solid as you think. In fact, sometimes particles just go right through it, not over, not around, through. That's quantum tunneling. This isn't just a weird trick of math or a sci-fi idea. It's real, and we've built working technology on it. Without tunneling, your phone's processor wouldn't even work. The sun wouldn't shine. And radioactive decay? That's tunneling too. So what exactly is going on here? In quantum mechanics, particles don't behave like tiny billiard balls. They act more like waves, clouds of possibility that can stretch, interfere, and bend. A particle, say an electron, doesn't just exist in one place until it's measured. It has a wave function, which is a fancy way of saying it has a chance to be in many places at once. Now imagine that particle is approaching a barrier, a region it normally shouldn't have enough energy to cross. In classical physics, it would stop cold, the wall wins. But quantum mechanics doesn't care about classical rules. The wave function of the particle actually extends slightly into the barrier, and even beyond it. That tiny extension means there's a small, non-zero chance the particle could be found on the other side. So, sometimes it is. The particle didn't break the wall, it didn't climb over it, it just slipped through like the wall wasn't fully real in the first place. That's the essence of tunneling. Reality is fuzzy, and particles can exploit that fuzziness to pull off what looks impossible. What's even wilder is how reliable this is. We can predict tunneling probabilities with astonishing accuracy. In fact, the STM, Scanning Tunneling Microscope, uses this exact principle. It brings a sharp metal tip extremely close to a surface. The electrons from the tip don't need to physically touch the atoms. They tunnel through the vacuum gap between the tip and the surface, creating a current we can measure. That current changes depending on what's underneath the tip, letting us see individual atoms. But quantum tunneling isn't just about cool tech. It's a glimpse into how thin the walls of our reality really are. In radioactive decay, for example, unstable atoms have trapped particles inside their nuclei. Classically, they shouldn't be able to escape, but tunneling gives them a way out. Over time, one particle might suddenly pop out through a barrier it had no business crossing, and the atom changes forever. Now think bigger. Some physicists think tunneling might have helped start the universe. The theory goes like this. In the earliest moments of the universe, the vacuum wasn't stable. It was trapped in a high-energy false vacuum, like a marble stuck in a shallow dent on a hill. Tunneling could have allowed it to escape to a lower energy state, releasing massive energy and driving cosmic inflation, the Big Bang's rapid expansion phase. In other words, tunneling might have helped reality become real. It gets even stranger when you add time to the mix. A particle can tunnel through a barrier faster than light would take to travel across the same space. It's not violating relativity, because no information travels faster than light, but it's unsettling. What does it mean for cause and effect if something can cheat the system and appear where it shouldn't be? And then there's the human brain. Some researchers wonder if quantum tunneling could be part of consciousness. That's still wildly debated, but the theory is this. Microtubules inside neurons might support quantum effects. If tunneling plays a role there, then decision-making and awareness might have roots deeper than biology, reaching down to the quantum level. That would mean even our thoughts could be influenced by probabilities slipping through invisible barriers. Of course, no one's proven that. But the mere possibility stretches our understanding of what's real and what's not. Tunneling reminds us that reality isn't solid. It's not as locked in as we like to believe. There are loopholes, chances, glitches, and those tiny slivers of possibility aren't just footnotes in physics textbooks. They're the reason stars burn, atoms decay, and life as we know it exists. So the next time something feels impossible, remember, at the smallest scales of the universe, the impossible happens all the time. Particles don't ask permission. They tunnel. Quantum entanglement and dreams. Is sleep a portal? There's something deeply mysterious about dreams. We've all had those moments, waking up from a dream that felt more real than life itself. You may forget your breakfast, but not that one strange dream where you met someone you've never seen before, yet felt you'd known them forever. What if dreams are more than psychological residue or neural static? What if dreams are actual journeys, interconnected through something far stranger than we've dared to imagine? This is where quantum entanglement enters the picture. At its heart, quantum entanglement describes a relationship between particles so intense that no matter how far apart they are, across a room, a planet, or even the galaxy, what happens to one instantly affects the other. It defies space, it defies time. But what if this strange physical principle doesn't just apply to atoms and photons, but to something within us? Let's start with what we know. During REM sleep, our brains enter a highly active state. Neural activity increases, the body goes still, and dreams begin. But unlike waking thought, dreams don't follow normal logic. We jump between scenes. We see symbols. We remember feelings more than facts. In some ways, dreams are the most quantum experience we can have. Chaotic, nonlinear, and sometimes timeless. Now here's where it gets even weirder. Some researchers have suggested that consciousness itself may rely on quantum processes. The Orc-Or theory, proposed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff, argues that quantum computations occur in microtubules, tiny structures inside brain cells. These quantum events might form the very basis of consciousness. If that's true, and consciousness has a quantum dimension, then what happens when we sleep? Could dreams be a side effect or a consequence of quantum processes connecting to something beyond our usual perception? Could our sleeping mind be slipping into a shared field of entanglement where the boundaries between our thoughts and someone else's begin to blur? People often report dreaming of someone only to discover that person had a similar dream the same night. This happens too often to be coincidence for some dream researchers. They call it mutual dreaming or shared dreaming. While skeptics write it off as randomness or bias, quantum physics suggests there may be more happening under the surface. If two brains are entangled, however briefly, perhaps through emotional connection, trauma, or even genetic links like twins or family, what's stopping dream states from acting as a temporary bridge between them? In waking life, our attention is grounded by the physical world. But in sleep, the noise fades. The filters loosen. Maybe then, the underlying quantum threads that connect us can be felt, or even seen. But it doesn't end with people. Some believe dreams also provide glimpses of events or places they've never experienced, past lives, future memories, alien worlds. Are these pure imagination, or is something else at play? In quantum theory, the future is not fixed. Until something is observed, it exists in a range of probabilities, a superposition of possible outcomes. What if dreams let us momentarily experience those probabilities, peeking into timelines that haven't yet unfolded? It's possible that dreams act like entangled echoes from different versions of ourselves, alternate paths our lives could have taken. In the multiverse interpretation, every choice splits reality into branches. Maybe dreaming is how we briefly sense those other selves. And entanglement is the bridge that lets us connect, however fleetingly, to them. Here's another angle. What about people who have profound dreams that change their lives? They wake up knowing something they didn't before. They dream about a distant relative's death before it happens. Or they come up with a solution to a problem they couldn't solve while awake. Is that intuition, or is it evidence of quantum information bleeding through? You see, in quantum mechanics, information is never truly lost. Even in black holes where nothing can escape, some believe entangled particles hold the key to recovering lost data. If dreams can access quantum information fields, non-local, timeless, interconnected, then it's no wonder some dreams feel like more than just dreams. Of course, this is still theory. No lab has measured a quantum entanglement between dreaming minds, at least not yet. But scientists are beginning to study quantum biology, the idea that living systems use quantum effects like tunneling and coherence. Birds may navigate with entangled particles in their eyes. Photosynthesis appears to rely on quantum efficiency. If plants and animals can use these mechanisms, why not the human brain? So, is sleep a portal? Maybe not in the sci-fi sense, but if consciousness is a quantum phenomenon, and dreams reflect consciousness unfiltered, then yes, dreams could be our most accessible portal to the quantum realm, a space where distance doesn't matter, where time bends, where memories, people, and possibilities all coexist in strange harmony. And perhaps late at night, when the world is still, and your mind begins to drift. You're not just dreaming, you're entangling with someone, with somewhere, with something beyond the veil of waking life. Zero-point field, the infinite sea beneath everything. They say space is empty, but what if it's not? What if, instead of being a vast void, the space between atoms, stars, and even thoughts is filled with something so fundamental, so constant, that we forget it's even there? This is the zero-point field, and no matter who you are or where you are, you're already submerged in it. Let's start simple. Imagine taking all the energy out of a system. Every particle stops moving. Everything is still. In classical physics, we'd call that the absolute zero point. No energy, no motion, just silence. But quantum physics doesn't play by those rules. Even at absolute zero, something remains. A jitter, a hum, a subtle vibration that never fades. That ever-present buzz. That's the zero-point energy. And it's not a quirk, it's a requirement, because quantum fields never truly sleep. According to quantum field theory, every point in space is buzzing with fluctuating fields. Even when there's no light, no heat, no movement, fields are still dancing. These fluctuations aren't noise, they're the foundation, the base level of reality. They're what's left when everything else is stripped away. This is the zero-point field, an ocean of potential, quiet, but never still. Now here's where it gets mind-bending. The Casimir effect is one of the first clues we had that this field is real. Place two metal plates extremely close together in a vacuum, nothing between them, absolute nothingness. But after a while, those plates start moving toward each other. Something is pushing them. But what? It's the zero-point field. Outside the plates, there's a full spectrum of quantum fluctuations. Inside, only specific wavelengths can fit between the narrow gap. That imbalance, it causes a pressure difference, and the plates are pushed together not by gravity, not by air, but by the sea of quantum energy itself. This field isn't just abstract math, it has force. Now zoom out, way out. Some physicists believe the zero-point field might be tied to dark energy, the mysterious force pushing the universe to expand faster and faster. If the zero-point field has energy, and it's everywhere, it could be influencing the cosmos on a massive scale. Some calculations even suggest the energy density of the vacuum could be enough to rip the universe apart if it weren't somehow balanced. But it's not just out there in deep space. It's in you, right now. The atoms in your body are surrounded by it. Some researchers even think our nervous systems, our thoughts, might interact with this field, that the field could store information, that it might even be a kind of cosmic memory, a universal archive of everything that ever was. Think about that. A field that remembers, a field that connects, a field that listens. And here's where it gets even weirder. In quantum mechanics, particles pop in and out of existence all the time. Virtual particles that appear, interact, and vanish. They're borrowing energy from the zero-point field just for a blink before giving it back. This process happens constantly, everywhere. It's not rare, it's normal. That means the vacuum isn't empty. It's boiling, teeming with activity we can't see. A foam of existence bubbling beneath everything. And there's a theory, still on the fringe but growing louder, that the zero-point field might be the fabric behind entanglement itself. That when particles become linked, they're not sending signals faster than light. They're tapping into the same ocean, surfing the same field. Distance becomes irrelevant when the medium itself is shared. Some call it the quantum ether. Others call it the matrix of reality. And then, there are those who believe consciousness itself is rooted in this field, that our thoughts are not just electrical pulses in a brain, but ripples in a sea. That when you meditate, dream, or feel a flash of intuition, you're syncing with it, like tuning a radio to the frequency of the universe. Whether or not that's true, the idea is powerful, that beneath everything we know, beneath space, time, and even thought, there is a field, not empty, not void, but full, endless, quietly shaping reality from behind the curtain. So, the next time you sit in stillness and feel like you're surrounded by nothing, remember, the zero-point field is there, always moving, always humming, always listening. And maybe, just maybe, it's the most important thing we've yet to understand. The double-slit experiment, when observation changes reality. If you were to pick one experiment that cracked open the weirdness of quantum mechanics, it's this one, the double-slit experiment. It's simple, it's elegant, and it absolutely wrecks your sense of reality. Picture this. You fire particles, let's say electrons, at a screen that has two vertical slits cut into it. Behind that is a detector screen that records where the electrons land. Now, if electrons behaved like little balls, you'd expect to see two bands directly behind each slit. That's what common sense tells us, right? But that's not what happens. When no one is observing, when we just let the particles fly without checking which slit they went through, the electrons act like waves, not particles, waves. And they interfere with each other, just like ripples in a pond. The result? A complex pattern of bright and dark bands on the detector screen, called an interference pattern. That's the signature of wave behavior. But wait, electrons are supposed to be particles, aren't they? Okay, now here's where it gets even weirder. Let's add a detector. Let's try to observe which slit the electron actually goes through. Surely, with modern equipment, we can know whether it took the left or the right path. Boom! The moment you turn on the detector, the interference pattern disappears. Suddenly, the electron stops behaving like a wave. It picks a slit, one, and it acts like a classic particle, as if it knows it's being watched. You read that right. The act of observation changes the outcome. Let that settle in for a second. When nobody's watching, the electron acts like it went through both slits at once. A wave of probability, a ghost of itself, spread across space. But the moment you measure it, observe it, or try to peek at its path, it collapses. It chooses. It becomes a single definite thing. And the strangest part, it's not the detector's physical presence that causes the change. It's the information. Even if the measuring device doesn't interfere directly with the particle in any classical sense, the knowledge gained from the observation is enough to collapse the wave. Reality, it seems, only solidifies when someone is looking. Some scientists call this the observer effect. But that phrase doesn't quite capture the cosmic insanity of what's going on here, because it raises a terrifying question. What if consciousness is fundamental to the universe? What if we play a role, not just in seeing the world, but in creating it? Let's go deeper. Some interpretations of quantum mechanics suggest that before observation, a particle exists in a superposition, a cloud of probabilities. It's not here or there, it's both, it's all. But once we measure it, the wave function collapses into a single outcome. Our conscious interaction with it selects a reality from the menu of possibilities. Is that what's happening? Or is there something even stranger afoot? The many worlds interpretation offers an alternative. It says that every possible outcome of a quantum event actually does happen, but in separate branching universes. In this view, the particle doesn't collapse. Instead, the universe splits. In one version, the particle went left. In another, it went right. Both outcomes exist, but you only experience one, which would mean that reality is constantly forking into infinite versions of itself, all triggered by observation. Then there's the idea that time might be playing tricks on us. Some theories suggest that the measurement not only affects the present, but reaches backward in time, reshaping the past. In delayed choice experiments, physicists have shown that choices made after a particle should have passed through the slits still affect whether an interference pattern appears. It's as if the universe is retroactively deciding what happened, based on what you choose to look for. And if that doesn't melt your mind, nothing will. Let's recap, not to conclude, but to make the mystery even deeper. A particle acts like a wave until someone observes it. Then, it acts like a particle. This means that reality itself may not be solid until it's interacted with, that at the smallest, most fundamental level, everything is a blur of probability until a conscious observer collapses it into certainty. It forces us to ask, is the universe real when no one's looking, or is reality a grand illusion waiting to be rendered? That's the double-slit experiment, simple on paper, infinite in implication. Planck scale mysteries, the pixel size of the universe. We often imagine space as smooth and continuous, but what if it isn't? What if, instead of being infinitely divisible, the universe is made up of the tiniest indivisible units, like digital pixels in a screen? That idea takes us into the realm of the Planck scale, the smallest possible scale of length, where the very fabric of reality begins to blur. And at this scale, everything we think we know about space, time, energy, and matter begins to fall apart. The Planck length is about 1.6 x 10 circumflex 35 meters. To put that in perspective, it's 100 million trillion times smaller than a proton. It's the scale at which the smooth laws of classical physics stop working. Space itself is no longer a fluid continuum. It becomes grainy, jittery, foamy. Some physicists believe that space and time might be quantized at this level. Not just things inside the universe, but space itself could be built from discrete units. You can think of it this way. Just as a digital photo looks smooth from afar, but reveals blocky pixels up close, our universe may appear continuous, but zoom in far enough and it becomes pixelated. These pixels of space might form the fundamental building blocks of the cosmos. You can't go smaller than the Planck length because, at that point, the very concepts of distance and location lose their meaning. But here's the strange twist. We can't measure anything at the Planck scale directly. Every attempt to probe it runs into a cosmic problem. If you try to examine something that small, you'd need so much energy that you'd create a black hole. The act of trying to see that deep into reality would collapse space on itself. It's as if the universe has locked that door and hidden the key. This brings us to an even wilder idea. Some physicists believe that the Planck scale is where gravity and quantum mechanics finally merge. We know gravity dominates the large-scale universe, stars, galaxies, black holes, but it's practically irrelevant on the atomic scale. On the other hand, quantum mechanics rules the tiny world of particles. And yet, for decades, scientists have tried to unify these two pillars of physics with no success. The answer might lie in the mysterious fuzziness of the Planck scale. At this level, space-time isn't a smooth curve. It ripples, fluctuates, and even tears. This is called quantum foam, a concept introduced by physicist John Wheeler. It imagines that the tiniest regions of space are not calm and still, but violent and chaotic, filled with constantly appearing and disappearing virtual particles, micro wormholes, and entangled loops of energy. In this foam, cause and effect become fuzzy, and time may flow both forward and backward. But if the Planck scale is like the pixel size of the universe, who set the resolution? This is where things get speculative, yet fascinating. Some theorists suggest that the entire universe could be a simulation running on a cosmic processor, and the Planck length is the universe's native resolution. Like a video game running at a certain frame rate, there's a minimum unit of space and time, and nothing happens in between. No movement, no change, no reality. It's not just philosophical musing. Some approaches to quantum gravity, like loop quantum gravity, literally describe space as being made up of finite loops, tiny quantized chunks of geometry that form a woven fabric. Think of a tapestry. It looks smooth until you zoom in and see the individual threads. That's how some physicists think space works at the Planck scale. Then there's string theory, which posits that all particles are tiny vibrating strings, and these strings are roughly the size of the Planck length. Go smaller than that, and the string has no inside left to explore. It's just vibration, and probability. The Planck scale becomes the edge of our universe's resolution. And now we arrive at the weirdest implication. If space is quantized, could the same be true for time? According to some models, there might be a Planck time, the smallest possible unit of time, about 5.39 x 10 circumflex 44 seconds. Below that, time as we know it doesn't exist. The flow of events breaks down. Everything freezes. This could help explain why quantum events happen probabilistically, because between one tick and the next, reality can't decide what it wants to be. It simply jumps randomly from possibility to possibility. And remember, every second you're alive, billions upon billions of these Planck scale ticks are flashing by, silently orchestrating the rhythm of the cosmos. The Planck scale isn't just about smallness, it's about limits. The ultimate speed limit, the speed of light, the ultimate minimum distance, the Planck length, the ultimate minimum time, Planck time, and the ultimate information content of space, like the holographic principle, all seem to connect here. So when you close your eyes tonight and drift into sleep, realize that beneath your bed, beneath your cells, beneath the atoms and quarks and strings, there's a cosmic lattice flickering at incomprehensible speeds, stitching the universe together pixel by pixel, tick by tick. And yet, somehow, it all feels smooth. Quantum Zeno effect, freezing time through attention. They say a watched pot never boils. But what if, in quantum mechanics, that's more than just an old saying? Welcome to the quantum Zeno effect, a phenomenon that suggests if you observe something often enough, you can stop it from changing. Literally. Time, frozen, not in some sci-fi way, but through the very act of measurement. It's one of the strangest, most mind-bending ideas in the quantum world. Let's break it down. In the everyday world, if you stare at a clock, time still ticks forward. A leaf still falls. A candle still burns. But at the quantum level, where particles dance in strange, probabilistic ways, watching something can trap it in place. The quantum Zeno effect says that if you measure a quantum system continuously enough, you can prevent it from evolving. The system gets stuck, unable to move forward in time, because the act of observation collapses its state again and again, faster than it can change. To understand this, imagine a particle that's in a superposition, meaning it's in multiple possible states at once. Let's say it has a 50% chance of being in state A and a 50% chance of switching to state B. If you leave it alone, it will evolve naturally, and over time it might end up in state B. But if you check on it constantly, every microsecond, something wild happens. Each time you observe it, the wave function collapses, and the particle resets back to state A. It never gets the chance to evolve. It's like it's frozen in time. This is not just a thought experiment. It's been tested. Physicists have conducted real-world experiments, like with ultra-cold atoms in magnetic traps, that show this effect in action. They've seen that by repeatedly measuring a particle's position or energy state, they can delay its natural evolution. And the more frequently they check, the more frozen the system becomes. It's like pressing pause over and over again before anything has time to happen. This phenomenon gets its name from the Greek philosopher Zeno of Elea, famous for his paradoxes about motion. You know the one, where a flying arrow frozen in each individual moment of time seems to never move at all. The quantum Zeno effect takes that paradox and gives it a bizarre quantum twist. It turns philosophical riddle into physical reality. But this isn't just a cool trick. The implications are huge. First, it challenges our understanding of time itself. If time at the quantum level can be slowed or even halted by observation, then what is time really? Is it a smooth, flowing river? Or is it a sequence of still frames like a film strip that only appears to flow when we stop watching? Second, it reveals how powerful observation truly is. In the quantum world, measuring something isn't passive, it's active. It changes the system. Observation isn't just a window into reality, it's a tool that reshapes it. Now here's where things get weirder. The quantum Zeno effect doesn't just work in isolation. There's also the anti-Zeno effect, where under certain conditions, observing a system frequently can actually accelerate its decay. That's right, watching something closely can either freeze it or speed it up, depending on how the measurements interact with the system's natural dynamics. This duality adds another layer of mystery. The act of observation is not neutral, it's more like interference. And in the real world, this could have practical uses. In quantum computing, where fragile qubits tend to decohere and lose information, the Zeno effect could be used to stabilize systems. By strategically watching the system, we might slow down unwanted changes, preserving coherence longer. It's like babysitting reality to keep it from drifting off. Some have even speculated about the philosophical and psychological angles. If reality is fundamentally changed by observation, then what role does consciousness play? Are we affecting the world just by paying attention? Could attention itself be a force? It's speculative, sure, but in quantum mechanics, the line between science and philosophy often blurs. And here's one final twist. What happens when we are the observed? If observing a system changes it, then could something else, some higher observer, be watching us? Could consciousness itself be entangled with the fabric of time in ways we don't yet understand? The quantum Zeno effect may sound niche, but it touches on deep questions. What is time? What is reality? And how much of it do we control just by being aware? This isn't just theory, it's a glimpse into the fragile edge between possibility and actuality. And it shows us that in the quantum world sometimes, just watching is enough to rewrite the rules. Time crystals, the newest form of matter that defies time. If you thought diamonds were forever, wait until you hear about time crystals. These are not science fiction. They're a real confirmed state of matter that defies one of the most basic rules we've always assumed, that time flows in only one direction and that matter follows along. Time crystals break this rule. They're not just weird, they're impossible according to classical physics, and yet they exist. A time crystal is a structure that repeats not just in space, like regular crystals, but in time. Picture a snowflake, symmetrical, beautiful, and repeating. Now imagine a snowflake that pulses in a rhythm over and over without any energy input. It's like a pendulum swinging forever without slowing down, not because it's powered, but because it's built into the laws of its existence. That's what makes time crystals so strange. They oscillate forever in their lowest energy state. This isn't supposed to happen. In the known laws of thermodynamics, especially the second one, systems always tend to move toward disorder. Energy spreads out, movement slows. Eventually, everything decays. Time crystals laugh in the face of this. They challenge the very core of what physicists thought they understood. The first theoretical prediction of a time crystal came from Nobel laureate Frank Wilczek in 2012. He asked a simple but radical question. Could a structure repeat in time in the same way a crystal repeats in space? At first, even physicists didn't take it seriously. It felt like a thought experiment, something destined to stay theoretical. But a few years later, experimental physicists found a way to make it happen using chains of trapped ions and quantum computers. In 2017, a team from the University of Maryland used a system of ytterbium ions, aligned like a row of tiny spinning tops. These ions interacted with each other in a controlled way, flipping back and forth in a stable, repeating pattern. This wasn't just a cycle, it was a time crystal. Then, in 2021, Google's quantum computing lab made headlines by confirming a time crystal behavior using their quantum processor, Sycamore. The impossible had become real. But how does it actually work? In a time crystal, a set of quantum particles is periodically disturbed, like tapping a piano key in rhythm. Normally, this would disrupt the system and add energy, but in a time crystal, The particles respond by settling into a rhythm of their own. They begin to tick in sync, but only at every other tap. It's like pushing someone on a swing and having them respond every second time, forever. That response happens in their ground state, their lowest energy. It's not costing them anything to do it. This break in time symmetry, responding at half the rate of the disturbance, is at the heart of time crystals. It's a violation of what's called time translation symmetry, the idea that the laws of physics stay the same over time. Time crystals show that under specific quantum conditions, time can become structured. It's no longer a smooth river. It can have ripples, echoes, repeating intervals. Now, why should you care? Because this isn't just a physics curiosity. Time crystals could revolutionize quantum computing. Their stable, repetitive nature makes them ideal for preserving quantum information over time. Think of them as a kind of perfect memory, always ticking, never changing, always predictable. They also open up questions that shake the foundations of science. If matter can defy time, what else might be possible? Could time crystals help us understand dark energy or even time travel? Are there systems in nature that already operate this way, unnoticed? Could consciousness at some level be linked to quantum processes like this? The more we learn about time crystals, the more they seem like a crack in the wall of classical reality. They're a reminder that the quantum world doesn't play by the same rules we do, and that time, which we've always seen as linear and unstoppable, might just be more flexible than we thought. So, as you drift to sleep, picture this: a crystal not of atoms frozen in space, but of time itself, gently ticking in silence, pulsing forever in a rhythm older than the universe and stranger than any dream. Entanglement and memory. Are our minds quantum receivers? Some scientists believe our brains are more than just biological computers. They might actually function as quantum receivers. And if that's true, then memory, something we usually think of as a physical process stored in neurons, might instead be entangled with something far beyond the brain itself. This idea begins with a strange observation. Human memory is inconsistent. Sometimes we remember things in perfect detail, other times entire moments vanish. And in some rare cases, people suddenly recall long-forgotten events with clarity, as if they were pulled from thin air. Could these moments of perfect clarity be linked to something deeper, something quantum? Let's start by looking at how entanglement works in physics. Two particles can be separated by vast distances, but if they are entangled, a change in one instantly affects the other. There is no signal sent, just instant correlation. This kind of connection defies our everyday understanding of time and space. Now imagine if thoughts, ideas, or memories could work the same way. Several researchers in the field of quantum cognition have proposed that the brain might use quantum processes, especially when it comes to how we remember, learn, and perceive reality. This doesn't mean your entire brain is behaving like a quantum computer. Instead, it suggests that certain small-scale processes, like those involving microtubules in neurons, could support quantum coherence for short periods. In 1994, physicist Roger Penrose and anesthesiologist Stuart Hameroff proposed the ORC-OR theory, short for Orchestrated Objective Reduction. Their idea was that microtubules inside neurons could sustain quantum superpositions long enough to influence brain activity, meaning consciousness might actually be rooted in quantum events. While the theory remains controversial, it's one of the first to link quantum mechanics to the mind. Now let's go a step further. What if memories are not only processed quantumly, but stored non-locally? That is, not just in your brain, but in a field. Something like the quantum vacuum or the zero-point field. If true, then retrieving a memory wouldn't just be about activating a synapse. It would be about tuning in to the right frequency, like finding a signal on a cosmic radio. This brings us to the idea of entangled memory. Think about this. When someone close to you passes away, Why do you still feel connected? Why do some people claim to receive messages in dreams or feel intense presence at random moments? Some scientists argue these could be products of grief or psychology, but others suggest a more radical view, that emotional bonds create real quantum entanglement between minds. In other words, when you form a deep connection with someone, you may become entangled on a quantum level. And long after that person is gone, the entanglement may still exist, meaning memory isn't just stored in your neurons, it's active in the fabric of the universe itself. This also aligns with certain findings in near-death experiences and psychedelic states. People report downloading vast amounts of information, remembering long-lost events, or even accessing memories from other lifetimes. From a classical neuroscience view, these stories sound impossible. But if we consider the brain as a receiver rather than a storage unit, suddenly things start to make more sense. Let's also touch on collective memory, sometimes called the morphic field, as described by biologist Rupert Sheldrake. He believes there's a kind of field around species that stores habits, behaviors, and patterns. A memory field accessible by all members of the group. Think of how birds know how to migrate, or how spiders instinctively spin webs. What if human beings also have access to this field? And what if our thoughts, memories, and dreams are partially formed by it? This theory gains some support from studies of entangled photons. In one experiment, when one photon's properties were changed, the other reacted, even though they were separated by kilometers. The information wasn't sent across space, it was shared instantly. Now imagine applying that same logic to consciousness. If we're entangled with others, with ideas, with information fields, could we be accessing memory not from inside, but from a quantum field that surrounds us? To be clear, this theory is still speculative, but it's gaining traction. Some physicists and philosophers believe consciousness cannot be explained purely by classical physics. The mystery of memory, how we recall, forget, and reconnect with the past, may be one of the clues leading us to a deeper, hidden structure of reality. So next time you remember something you haven't thought about in years, something that just appears in your mind like a whisper from the past, ask yourself this: where did that memory come from? And what if your brain didn't store it but received it? The quantum brain hypothesis. Are we thinking in qubits? For decades, neuroscientists have mapped our thoughts to neurons, synapses, and chemical reactions. It's a tidy system, electric signals bouncing between brain cells, guiding memory, logic, emotion. But there's a theory that says this model might be missing something big, something truly bizarre, the possibility that our brains aren't just biological processors, but quantum ones. This is the quantum brain hypothesis. It proposes that our brains might not only function through classical biological means, but also exploit principles of quantum mechanics, like superposition and entanglement, to achieve consciousness, thought, and memory. At first, this sounds impossible. After all, quantum systems are fragile. They usually exist in isolated environments at near absolute zero, protected from any external noise. Our brains, in contrast, are warm, wet, and noisy. They're constantly pulsing with electrochemical activity, bathing in blood flow, and reacting to every heartbeat and breath. But here's where things get weird. In the 1990s, physicist Roger Penrose and anesthesiologist Stuart Hameroff proposed a groundbreaking theory called orchestrated objective reduction, OR. They suggested that microtubules, tiny structural components inside neurons, might be sites of quantum computation. That means these minuscule fibers could act like qubits, holding information in multiple states at once. According to their theory, the collapse of these quantum states inside microtubules could give rise to conscious thought. In essence, your awareness might emerge not just from neuron firing patterns, but from quantum events playing out in the background, hidden inside the scaffolding of your own brain cells. This would mean your thoughts are not strictly linear or deterministic. Instead, they could arise from probabilistic processes where possibilities exist simultaneously before settling into reality. In a sense, your mind could be surfing a quantum wave function, and your decisions might reflect a collapse of that wave, just like a particle observed in a lab. Still, many scientists were skeptical. They argued that the brain's environment is too chaotic to sustain quantum coherence, the delicate state needed for quantum computing. Decoherence would happen too fast, disrupting any quantum effects before they could influence thought. But then came some surprising evidence. In 2014, a team of researchers at the National Institute of Material Science in Japan found that quantum coherence could persist in warm biological conditions, specifically inside avian compass proteins. Birds like robins are thought to use entangled particles in their eyes to navigate Earth's magnetic field. If quantum coherence can exist in a bird's eye, could it also exist in a human brain? And there's more. Recent studies in quantum biology suggest that photosynthesis, enzyme reactions, and even olfaction, the sense of smell, may use quantum effects. If nature already utilizes quantum processes in other living systems, the idea of quantum activity in the brain doesn't seem so far-fetched anymore. Some experiments have also detected unexpected quantum behavior in the brain. In 2020, a study from MIT and the University of Chicago observed strange electromagnetic signals coming from human neural tissue that couldn't be fully explained by classical models. The signals hinted at coherence and phase locking, concepts more at home in a quantum lab than in a brain scan. Now, this doesn't mean our thoughts are teleporting through space or that we're entangled with other people's minds, although intriguingly, some researchers have speculated about that too. The truth is, if our brains do process information using quantum principles, it could explain some of the strangest features of consciousness, how we form intuition, experience déjà vu, or make lightning-fast decisions with minimal data. In classical systems, decisions are step-by-step, like a computer executing code. But in quantum systems, the answers can be processed in parallel, in superposed states, and then snapped into place. Maybe that's why our brains can arrive at solutions instantly, before we're even aware we're thinking. Quantum computing is already showing how powerful this kind of thinking can be. Companies like Google and IBM are racing to build quantum machines capable of solving problems that classical computers never could. If evolution has been working with quantum systems for millions of years, the human brain might already be the most advanced quantum computer on the planet. Of course, none of this is fully proven. The quantum brain hypothesis remains controversial. Critics demand stronger evidence. Supporters say the tools simply aren't good enough yet to detect these fleeting quantum signals, but the implications are staggering. If our minds are quantum, it would redefine neuroscience, psychology, artificial intelligence, even spirituality. It would mean consciousness isn't just a side effect of matter, it's a quantum property of reality itself. Your thoughts wouldn't just be electricity, they'd be waves of possibility collapsing into your experience of now. It's a theory that collapses the boundary between brain and cosmos. And the question lingers. When you think, are you computing, or are you collapsing a quantum universe inside your own skull? Retrocausality. Can tomorrow shape yesterday? It sounds impossible, right? The idea that the future could somehow reach backward and alter the past. Yet, in the world of quantum physics, this isn't just a sci-fi concept. It's a real and growing field of curiosity. Retrocausality, as strange as it sounds, asks one fundamental question. Does the arrow of time only move forward, or is there more to the story? Let's start with what we think we know. Time moves forward. You wake up, eat breakfast, go about your day, and eventually fall asleep, cause followed by effect. We're trained to see time as linear. One event causes the next. But quantum experiments are starting to crack that belief. Enter the delayed choice quantum eraser experiment. In it, a photon is fired toward a screen with two slits, left open to interfere with each other. Usually, if no one observes which slit it goes through, you get an interference pattern. But if you observe the path, the interference disappears. Here's the kicker. If you decide to observe the path after the photon has already hit the screen, the interference pattern still vanishes, as if your future choice influenced its past behavior. This isn't just a mind game, it's a real test. And it implies something shocking. The photon behaves as if it knows what you're going to do, even though the decision happens after it already took action. It's retrocausality in motion, future choices shaping past events. But how could this be possible? One interpretation is that time, at the quantum level, isn't linear. It's more like a tangled web. Past, present, and future may all be connected in ways we can't yet fully understand. Instead of a single line, time might be a loop or even a block where everything, every moment is happening simultaneously, but we only experience it one slice at a time. Physicist Yakir Aharonov proposed a fascinating idea called the two-state vector formalism. In it, a quantum system is defined not just by its initial state, as we typically do, but by both an initial and final state. This means the present is shaped by both past and future boundary conditions. Think of it like a movie. We understand the current scene better when we've seen the ending. In this framework, quantum particles are not only evolving from past to future, but also from future to past. It's not that your decision tomorrow changes what happened yesterday, but that both are part of a larger whole, woven together in a more complex structure than we usually consider. Now, let's ask the big question. Does this have any meaning for us beyond physics? Some thinkers suggest that if retrocausality is real, then intentions or future states of consciousness could play a hidden role in how the universe unfolds. In other words, your future state, your awareness, your decisions could ripple backward and affect moments that already occurred. While this isn't scientifically proven, it raises fascinating philosophical questions. For example, have you ever had a moment where something just felt fated, like your future self was somehow guiding you, nudging you? Could this be more than intuition? Could retrocausality allow future versions of ourselves to subtly influence the past, creating loops of learning, healing, or change? Even in the world of dreams, some people report seeing events before they occur. Is that merely coincidence, or a window into a deeper connection between timelines? There are also potential applications in quantum computing. Some experimental designs try to harness retrocausal behavior to reduce errors and increase speed. By allowing systems to know future outcomes and adjust past decisions accordingly, computers might become dramatically more powerful. We're only scratching the surface here, but the possibilities are enormous. Critics argue that retrocausality violates causality and opens up paradoxes. What if you went back and stopped your own birth? But in quantum mechanics, these kinds of paradoxes often resolve themselves through probability, not certainty. In retrocausality, you don't change the past, you complete it. Your choices were always part of the timeline, even if they seem to come later. It's like the universe is one gigantic puzzle already solved. Our lives are just the process of uncovering each piece in an order that feels linear, even if it's not. So, can tomorrow shape yesterday? In quantum theory, the answer isn't a firm yes, but it's certainly not a firm no either. What we know is that the fabric of time is far stranger than we ever imagined, and we may not be moving through it. It might be flowing through us. Now let's bring this to the quiet space where your mind rests. As you drift off, just consider this. What if your dreams tonight aren't just memories being sorted, but signals sent backward, messages echoing from the future, gently nudging your present into alignment? Sleep well, or perhaps wake up to a new yesterday. Holographic memory. Are our minds fragments of a bigger field? We think of memory as something stored in our brains, neurons firing in patterns, synapses storing our past like files on a hard drive. But what if that's not entirely true? What if memory isn't stored in your brain, but accessed, like a radio tuning into a signal? That's the wild but increasingly plausible idea behind holographic memory. Let's start with what a hologram actually is. A hologram is a 3D image encoded on a 2D surface where every piece contains the whole. If you break a hologram into fragments, each tiny shard still contains the full image, just blurrier. It's as if information isn't localized but spread out, distributed across the entire surface. Now take that concept and apply it to consciousness. According to the holographic brain theory originally proposed by physicist David Bohm and neuroscientist Carl Pribram, your brain might not actually store memories the way we think. Instead, it acts more like a lens, decoding information from a deeper field, a field that exists beyond space and time. This is where things get strange. If this theory holds any truth, then every memory, every thought, and even every moment of awareness could be a projection, not from inside your skull, but from a larger dimension of reality. Your brain would be like a receiver, not a warehouse. This helps explain some of the biggest mysteries in neuroscience, like why people with severe brain damage can sometimes retain full memories, or why during near-death experiences some people recall their entire lives in crystal clarity, faster than their brains could possibly process, or how savants, people with limited cognitive function, can perform impossible feats of memory or calculation. If memory were truly local, stored only in the brain, these things would be anomalies. But if the mind taps into a non-local field like a hologram, these miracles start to make sense. Let's take it further. In a holographic system, distance doesn't matter. Every point is connected to every other point. That sounds suspiciously like quantum entanglement, where particles remain linked across vast distances, sharing information instantly. Could our minds be operating on the same principles? Experiments in quantum biology suggest this isn't as far-fetched as it sounds. Plants and animals might already be using quantum effects to navigate, heal, and even sense things we can't explain. If memory taps into a field outside the brain, quantum mechanics could be the bridge that connects biology to consciousness. But there's more. If your memories are part of a holographic field, then you're not the owner of these memories. You're the access point. And that implies something profound, that memory might be collective. Carl Jung called it the collective unconscious, a hidden layer of shared knowledge, archetypes, and patterns we all carry. The holographic memory theory could be the mechanism behind it, a field that stores not just your personal memories, but the entire history of life, evolution, and maybe even the universe. Think about déjà vu, or the feeling of remembering something you've never experienced. What if these aren't errors, but glimpses into the shared field? What about past life memories in children, or those eerie moments when you feel like you're remembering the future? Could these be bleed-throughs from a deeper source, a holographic database beyond our linear perception of time? Even dreams start to look different under this lens. Maybe we aren't just making up stories at night. Maybe, just maybe, dreams are how we explore the field, unconsciously tuning in, downloading fragments of something greater than ourselves. This could also explain why certain meditative or altered states allow people to experience universal visions, things they couldn't possibly know, why people in different cultures see the same symbols, the same figures. If we're all accessing the same holographic field, then these experiences aren't hallucinations. They're broadcasts. Now here's the twist. If the universe itself is holographic, a theory many physicists are starting to entertain, then your memory isn't the only thing that works this way. Reality might be structured like a hologram. Everything we see, hear, and touch might just be the projection of a deeper, more fundamental layer. a dimension not defined by space, but by information. In this model, the boundaries between brain and mind, self and other, inside and outside, start to blur. You're not just a person in the universe, you might be a fragment of the universe becoming self-aware. Which means the memories you access aren't simply yours. They're the echo of a much bigger story. So the next time you recall a dream, a smell, a flash of childhood, ask yourself, is this really coming from within me? Or am I reaching into something infinite, something that's always there, waiting for us to remember? Tachyons, imaginary particles that travel backwards in time. The idea of tachyons first emerged in the 1960s, hypothetical particles that, unlike anything else, always move faster than light. In fact, by their very nature, they cannot slow down to the speed of light. To do so would mean losing all their energy, and theoretically they'd cease to exist. But even more peculiar is their link to time. They don't just race through space, they appear to move backward through time. Tachyons were born from equations in special relativity that allowed for imaginary mass. Imaginary, not as in fantasy, but in the mathematical sense involving the square root of -1. If a particle were to have this type of mass, the equations implied it wouldn't slow down as it lost energy. Instead, it would accelerate, forever staying above the speed of light. It sounded wild, but not impossible. That's all it took for theorists to take the idea seriously. And the implications? They're vast. If tachyons exist, they could, in theory, send signals back in time. A tachyon emitted today might arrive yesterday. This would break the very notion of cause and effect. If a message from the future can arrive in the past, it opens the door to paradoxes, the same kind that haunt time travel debates. Could you prevent an event that causes your message in the first place? Would that create a loop, or worse, a contradiction? Tachyons also show up in quantum field theory. Though we've never observed one, they're used as a kind of marker, a sign that a system is unstable. In string theory, when a tachyon appears in a model, it typically means the theory needs adjustment. It's like nature's way of saying, this configuration doesn't work, try again. In this sense, tachyons aren't real, but they're useful. They guide physicists toward better theories. But some physicists didn't want to stop at useful fiction. In the 1970s and 80s, researchers explored whether tachyons could be actual particles. Could they be harnessed? Could they explain mysteries in quantum mechanics? Some thought they might help solve the problem of quantum entanglement, why two particles seem connected across space instantly. Maybe tachyons were the invisible messengers. But this hope faded. As our tools became more precise, no evidence of tachyons showed up, no signals traveling faster than light, no signs of reversed causality, not even a trace of a particle with imaginary mass. It seemed tachyons, if they existed, were masters of disguise or simply didn't exist at all. Still, the idea won't go away. In fact, it keeps finding new life in theoretical physics. Some speculative models of the universe still use tachyons to explain phenomena like dark energy or even inflation, the mysterious force that made the universe expand faster than light after the Big Bang. If something like tachyons were present in the early universe, maybe that explains the rapid expansion. In sci-fi, tachyons became a favorite tool for time travel. They're mentioned in Star Trek, Doctor Who, and countless novels. Need a way to send information to the past? Just beam some tachyons. The science behind them might be shaky, but the idea is just too tempting to ignore. More recently, researchers have looked into the idea of tachyon condensation. It's a process where a tachyon field evolves, removing instability and settling into a stable state. It's like a stretched rubber band snapping back into place. Though we still lack evidence for real tachyons, this concept helps shape how we think about symmetry, vacuum states, and even the birth of the universe. One thing's clear: tachyons challenge our understanding of time itself. If backward time travel is even theoretically possible, it forces us to rethink the flow of time as we know it. Maybe past, present, and future are not as separate as they seem. And maybe, just maybe, there are particles out there racing faster than light, quietly rewriting the timeline in ways we can't yet detect. The Bohmian interpretation, the hidden wholeness of reality. There's a theory in quantum mechanics that doesn't make the headlines like many worlds or spooky action, but it's arguably one of the most quietly profound. It's called Bohmian mechanics, or more poetically, the pilot wave theory, named after its creator, David Bohm. Unlike other interpretations of quantum physics, Bohm's theory doesn't rely on probability and randomness as the core of reality. Instead, it insists on something deeply comforting and deeply strange, an invisible order guiding everything, hidden just beneath the surface of what we can measure. In traditional quantum theory, particles don't have definite positions until they're measured. But in Bohmian mechanics, particles always have a position, always. They move along defined trajectories, like little boats on a river. But here's the twist. The river itself is made of a wave, not a wave in water or air, but in something much stranger, quantum potential. And this wave isn't just local, it stretches across the entire universe. Everything, everywhere, is subtly interconnected through this wave. This is the pilot wave, and it pilots the particles. This idea offers a totally different way of understanding the uncertainty in quantum mechanics. In standard theory, the weirdness comes from nature being inherently unpredictable. But in Bohmian mechanics, it's not that nature is random, it's that we just don't see the whole picture. The randomness is just a symptom of our ignorance of the pilot wave's hidden structure. Imagine trying to understand the flow of a river by only looking at a single water droplet. That's what most physics does. Bohm's theory says, zoom out, look at the whole current. And that's where it gets deep. Because this pilot wave doesn't exist in space, it defines space. It's like an implicate order, as Bohm called it, a deeper layer of reality folded beneath the explicit order we see around us. The implicate contains the whole, everything, and unfolds it into the world we experience. It's like the world is being projected from this deeper dimension where all things are enfolded into one another. Let that sink in. Reality as a projection from a deeper, invisible whole. Sounds a lot like a hologram, doesn't it? This ties into another wild implication. Since the pilot wave is non-local, it instantly connects particles no matter how far apart they are. If you change the conditions for one particle here, the wave updates everywhere instantly, even across galaxies. The interconnectedness is not metaphorical. In Bohm's view, the universe is not a collection of isolated bits of matter bouncing around. It's more like a vast, flowing organism, a living totality where every part contains the essence of the whole. And in this totality, consciousness might not be a side effect. Bohm believed the mind itself could be part of the implicate order. The brain might be operating as a kind of receiver or processor of the deeper wave dynamics. Thought and matter could be two sides of the same flowing, enfolded field. This offers a radically different vision of existence. We're not separate, isolated beings navigating a dead, random universe. We are wave-guided patterns in a conscious, interconnected field of unfolding order. But why isn't Bohm's interpretation more widely accepted? Part of it is historical. It challenges the Copenhagen interpretation, which dominated the 20th century. It also introduces elements that feel philosophically uncomfortable, like determinism or the existence of a hidden realm that we can't directly measure. Bohm's theory is mathematically equivalent in predictions to standard quantum mechanics, but it redefines what's actually happening behind the curtain, and for many physicists, that curtain is best left untouched. But for those who dare to peek behind it, Bohmian mechanics offers a strangely reassuring view. The universe is not chaos, but coherence. Beneath the randomness, there's guidance. Beneath the separation, there's unity. Beneath the visible, there's a hidden wholeness from which all things flow, and it's not about particles or waves anymore. It's about the deep geometry of being itself. It's about a universe that isn't indifferent or accidental, but one that's whispering to us, through every entangled atom, that it is one. And we are part of it. The quantum soul theory. Does consciousness survive death? Some scientists believe the answer to life after death may not lie in philosophy or religion, but in quantum physics. It sounds outrageous at first. How could something as cold and mathematical as quantum mechanics possibly touch on something as emotional and personal as the soul? But here's where it gets strange. For years, researchers like Dr. Stuart Hameroff and physicist Sir Roger Penrose have explored the idea that human consciousness is more than just brain activity. It may be a quantum process. And if that's true, then death might not be the end. Let's break this down. According to the quantum soul theory, the key lies in tiny structures inside your brain cells, called microtubules. These are microscopic tubes that help organize the internal structure of cells. In neurons, they're especially dense. Hameroff and Penrose believe these microtubules are more than scaffolding. They're quantum devices. Inside these microtubules, they say, quantum information is processed. This goes beyond just electrical signals. This is quantum coherence, the strange dance of particles that are entangled, uncertain, and deeply connected across space and time. Now, why does this matter? Because if consciousness is rooted in quantum mechanics, then it follows different rules than classical biology. Quantum particles don't just vanish when a system shuts down. They can store information in a state of superposition, exist in multiple possibilities at once, and, most importantly, they don't easily lose information. In fact, one of the most haunting puzzles in physics is the black hole information paradox. According to quantum theory, information can never be destroyed. So, if you throw something into a black hole, where does the information go? Scientists still argue about that. Now apply that same logic to death. If your consciousness is just brain chemistry, it dies with the body. But if it's quantum, then the information, the you behind your thoughts, might remain. Not in your body, but somewhere else. Theoretically, it could be released back into the universe. Hameroff describes it this way. When someone dies, the quantum information stored in the microtubules doesn't disappear. Instead, it disperses. It leaks back into the quantum field, like a ripple going back into the ocean. And if that person is revived, that quantum information could return to the microtubules and the person might come back. Perhaps that explains near-death experiences. But even if there's no return, what happens to that ripple? That's where the theory turns almost poetic. This dispersed quantum information could, in theory, exist indefinitely, floating in the vast quantum field, waiting, maybe even combining with other fragments. Does that mean reincarnation? Not exactly. But it opens a door to the idea that consciousness might not be tied forever to a body, that you might be more like a signal than a structure, a frequency, not just a machine. Of course, many scientists remain skeptical. The brain is warm and wet, conditions usually hostile to fragile quantum states. Yet, studies in quantum biology show that certain biological systems like photosynthesis in plants or navigation in birds use quantum processes. If they can do it, why not our brains? Even more intriguing is that this theory echoes ancient beliefs. Some spiritual systems have long claimed that the soul is eternal, that consciousness survives death, that there is a deeper realm of being. Could quantum physics be the bridge between science and spirituality? Let's go deeper. There's an idea in quantum physics called decoherence. When a quantum system interacts with its environment and loses its quantumness. In the body, this would be death. But in the quantum world, decoherence doesn't mean disappearance. It just means change. The system transitions into a different state. So what if death is just quantum decoherence of the soul? It's not proof, it's not certainty. But it's a theory rooted in the math and mechanics of the very universe itself. It suggests that you, me, all of us may be more than flesh and thought. We might be patterns of information entangled, encoded, and preserved in the deepest layer of reality. In this view, death is not a wall. It's a veil, a shift from local consciousness to non-local existence. And if that's true, then maybe nothing is ever truly lost, not even you. Quantum superposition and the self. Are you more than one person? We often think of ourselves as singular beings, a single identity, a single stream of thoughts, a single consciousness. But quantum physics throws a wrench into this idea. One of its strangest principles is superposition, the ability of particles to exist in multiple states at once until they're observed. What if, just like particles, the self is not as singular as we believe? What if you right now exist in more than one version simultaneously? Let's start with the basics. In quantum mechanics, a particle like an electron doesn't exist in just one place or state. It exists in a superposition of many possible states. It's only when we observe it that it collapses into one. Before that, it's all possibilities at once. You might have heard this explained with Schrödinger's cat. The cat in the box is both dead and alive until the box is opened. Now apply that concept to identity. Your mind processes many thoughts, desires, fears, and ideas all at once. You might feel love and anger at the same time. You might want to stay and leave, decide and hesitate. In the classical view, we assume the brain picks one final you. But what if that's an illusion? What if the mind operates more like a quantum system than a mechanical one? Some cognitive scientists and quantum theorists believe that consciousness may exhibit a kind of quantum behavior, not in the sense of magical thinking, but structurally. Your brain is constantly weighing possibilities, and some theories suggest that this state of uncertainty, this ambiguity, might literally reflect a kind of quantum superposition. That you exist in a blend of mental states that only collapses into action when a decision is made. Let's go deeper. Consider dreams. In a dream, you can be yourself and someone else at the same time. You can remember your past, experience a future that hasn't happened, or take on a different role entirely. Could dreams be a peek into the many yous that exist in your subconscious? A realm where the mind allows different versions of you to coexist without contradiction. Now let's bring in parallel realities. If the multiverse or many worlds interpretation is true, then every choice you've ever made has spawned an alternate version of you. There's a version of you that took a different job, moved to a different city, said yes instead of no. If all these versions exist, are they entirely separate or are they entangled? Could they be part of a greater meta-you that exists across all timelines? Superposition also helps explain inner conflict. When you feel torn between two decisions, maybe it's not just emotional struggle. Maybe it's your consciousness existing in a temporary superposition between outcomes. It's only when you act that your mind collapses into a singular path. But that doesn't mean the others disappear. They still exist within you, like echoes or shadows of what could have been. This opens the door to another thought: identity fluidity. We often hear that people reinvent themselves or feel like different people in different contexts. Maybe they're not pretending. Maybe they're tuning into different versions of themselves that have always existed. In quantum terms, they're accessing alternate selves that are just as real as the one speaking right now. Even memory plays a role. Memories are not fixed. They change each time we recall them. So do emotions, habits, and perceptions. If your own memory of yourself can shift, who are you really? Maybe you're not a fixed point, but a constantly collapsing wave of possibilities. Let's not forget entanglement. If your consciousness is entangled with others, family, friends, even strangers, then perhaps the self is not isolated at all. Perhaps you is a network of connections, each one influencing and reflecting another. The idea of a separate enclosed self starts to fade. In this view, selfhood isn't a single candle in the dark, it's a shimmer, a probability cloud, a quantum field of identity that is fluid, overlapping, and deeply mysterious. You are many, and you are one, at the same time. And here's the strangest part. That might be the normal state of being. The illusion is thinking we're just one person, but the truth? That might be too big for one timeline, one body, or one name to hold. Vacuum fluctuations. When nothing isn't nothing. You've probably heard the phrase, out of nothing something came. But what if that nothing was never really empty to begin with? In the world of quantum physics, the vacuum, the supposed blank canvas of space, isn't a void. It's a seething froth of activity, bursting with tiny, fleeting events that defy everything we assume about nothingness. This idea is called vacuum fluctuations, and it suggests that even the emptiest parts of space are anything but. At its core, a vacuum fluctuation is a temporary change in the amount of energy at a point in space, caused by the uncertainty principle. That principle, formulated by Heisenberg, says we can't precisely know both the energy and the time associated with a system. So, for short periods of time, energy can seemingly pop into existence, borrowing from nowhere, returning quickly, and leaving no trace. These momentary appearances of energy give rise to virtual particles, particles that flicker into and out of existence faster than we can observe them directly. It's a ghostly ballet. For the tiniest slice of time, a pair of particles, say a particle and its antiparticle, materialize from the vacuum, interact briefly, and annihilate one another. They're not real in the sense that we can isolate or observe them like ordinary matter, but their effects? Those are very real, and in fact, this ghostly quantum flickering is responsible for one of the strangest phenomena ever predicted and later confirmed in physics, the Casimir effect. If you place two uncharged metal plates extremely close together in a vacuum, they will experience an attractive force, even though no particles or energy seem to be pushing them. The cause? Virtual particles between the plates are limited in the wavelengths they can take due to the narrow gap. Outside the plates, more virtual particles are buzzing freely. The imbalance creates pressure, nudging the plates toward each other. Empty space, it seems, has pressure, but the implications stretch even further. Consider Hawking radiation, the process theorized by Stephen Hawking, in which black holes slowly evaporate over time. According to the theory, near the event horizon, a pair of virtual particles might form. One particle falls into the black hole while the other escapes, becoming real in the process. That escaping particle carries energy away from the black hole, causing it to slowly lose mass. In essence, the black hole is radiating, leaking away through the whisper of quantum nothingness. Then there's the question of the universe's expansion. The vacuum, it turns out, might be responsible for that too. The idea of dark energy, a mysterious force accelerating the expansion of the cosmos, could be rooted in vacuum fluctuations. The vacuum isn't static, it has energy. And that energy might be pushing the universe outward faster and faster. It's humbling to think that the most powerful force in the cosmos may come not from stars or gravity, but from what appears to be empty space. Vacuum fluctuations also play a central role in quantum field theory, a framework that describes all particles as excitations of their respective fields. Even when there are no excitations, no particles, the field is still there, still alive, still humming with possibility. A quiet field isn't truly silent, it's just waiting. And that waiting isn't passive, it's creative. Some physicists even speculate that entire universes could be born from vacuum fluctuations. If enough energy condenses in the right way, a region of space could inflate, break symmetry, and begin expanding as its own cosmos. It's a radical idea, but one that blurs the line between physics and metaphysics. What if the universe we're living in began as a fluctuation in someone else's vacuum? And this isn't just speculation for the chalkboard. We build quantum technologies based on vacuum behavior. Quantum computing, quantum cryptography, and even laser systems rely on our ability to work with and sometimes suppress these fluctuations. Vacuum isn't empty. It's usable. It's vibrant. It's part of our technological reality. Philosophically, the concept challenges our deepest intuitions. We've always imagined nothing as a clean slate, a blank void. But quantum physics whispers something stranger. Nothingness doesn't exist. What we thought was stillness is activity. What we assumed was silence is noise. Just too faint, too quick, too strange for our senses. In a way, vacuum fluctuations are a mirror. They reflect how little we truly understand about the foundations of reality. They suggest that beneath the calm surface of nothing, reality is endlessly alive. And maybe so are we. De Broglie-Bohm theory of the ghostly pilot wave behind everything. In the early 20th century, as physicists scrambled to make sense of the strange new world of quantum mechanics, a French physicist named Louis de Broglie offered a radical idea. Particles, like electrons or photons, are not just points, but also waves. This dual nature became one of the cornerstones of quantum theory. But de Broglie didn't stop there. What if there was a pilot wave guiding every particle, an invisible hand steering matter through the quantum fog? Decades later, David Bohm revived this concept, and together their ideas formed what we now call the de Broglie-Bohm theory, also known as the pilot wave theory. This theory doesn't rewrite the math of quantum mechanics. Instead, it gives us a different way to interpret the same equations. In standard quantum mechanics, particles exist in a haze of probability until they're observed. But in the de Broglie-Bohm view, particles always have a definite position. They're just being subtly pushed and pulled by an underlying wave. Imagine a leaf floating on a river. The leaf has a precise location at any given moment, but it's guided by the ripples and currents beneath the surface. That's what the pilot wave is, a river of information that determines how particles move, even if we can't see it directly. One of the most striking things about this theory is that it restores determinism to quantum physics. In the Copenhagen interpretation, outcomes are fundamentally random, but in Bohm's version, everything is still governed by cause and effect. The apparent randomness of quantum events is just a reflection of our ignorance. We don't know the full state of the pilot wave or the hidden variables involved. But this ghost wave isn't just pushing one particle. Here's where things get even stranger. In the de Broglie-Bohm framework, the pilot wave can connect multiple particles across space. Entanglement becomes a matter of shared guidance, a common wave function steering both particles, no matter how far apart they are. This allows the theory to explain non-local behavior without abandoning realism. There's a philosophical beauty in this idea. Rather than particles popping in and out of uncertainty, or multiple universes branching off at every moment, the pilot wave gives the universe a quiet, consistent flow. It suggests that reality is not fractured or random. It's just hidden from us. Still, the theory hasn't taken over mainstream physics. Why? Mostly because it adds complexity without producing new predictions. Every result you get from the pilot wave theory, you can also get from the standard quantum framework. It doesn't contradict experiments, it just explains them differently. And in physics, if two models give the same results, scientists often stick with the simpler one. But simplicity is subjective. For some, the de Broglie-Bohm theory offers clarity. It provides a picture of what's really going on when an electron passes through two slits. Instead of saying the particle is in a ghostly blur until we look, this model says the particle went through one slit and the pilot wave went through both. It's the wave that interferes with itself and shapes the particle's path. The interference pattern is baked into the wave, not created by observation. The pilot wave also redefines the role of the observer. In standard quantum mechanics, measurement collapses the wave function. In Bohm's version, there's no collapse, just continuous evolution. The act of observing is just another physical interaction, not a mystical interruption of the quantum flow. And then there's the question of the wave itself. What is it? Where does it live? It doesn't exist in 3D space like particles do. It lives in a higher dimensional space called configuration space, which represents all possible arrangements of all particles. It's like a cosmic roadmap, charting how every particle relates to every other. In that sense, the pilot wave isn't just guiding particles, it's shaping the entire dance of the universe. Some critics argue that this configuration space makes the theory too abstract. Others say it's no more abstract than the standard interpretation. It just puts the weirdness in a different place. But there's no denying the elegance of a universe where particles follow paths, guided by waves that ripple through a hidden dimension. And perhaps the most tantalizing part? The de Broglie-Bohm theory doesn't need parallel universes, doesn't require particles to be smeared out like fog, and doesn't make reality dependent on human observation. It offers a coherent, if subtle, picture of a universe that is both mysterious and grounded. In the end, the pilot wave theory is less about rewriting quantum mechanics and more about reframing it. It reminds us that the strangeness of the quantum world doesn't come from the math. It comes from how we choose to interpret it. And maybe, just maybe, the ghostly wave behind everything is more real than we think. Good night.